Good morning, everyone. Good afternoon, everyone. Yeah, I'm fine, fine. How are you all? Good afternoon. Good afternoon. Right. Let us start the topic, electronic measurements. Right. Before starting the actual topic, I would like to give the introduction. Let's see. First of all, let me know how many of you have attended my electrical measurements class. Electrical measurements class. Kindly raise your hand. Don't type any message, kindly raise your hand. Okay, right. Okay, many people are new, it seems. Right. Those who are not attended my electrical measurements, no need to worry, right? So I'm taking electronic measurements. There is no that much link, but even though some link is there, I will brush up all the points, no need to worry, right? Now, few people are still joining. Am I audible? Am I visible? Is screen visible, guys? Am I audible? Okay, right, right. Thank you, thank you. Perfectly fine. Okay, right. Newcomers, no need to worry. This is Ramesh. Many people attended my electrical measurement. They know my name. Other new people I'm giving. This is Ramesh. I'm taking measurement subject, electrical as well as electronic measurements. But for few people, electrical measurement is being done already. Now I'm taking electronic measurements combinedly. And those who are not attended electrical measurements, that will be taken later, no need to worry. Right? First of all, in these electronic measurements, what is the syllabus? And what are the corresponding topics available one by one? I'll give the introduction. By the time other people will join, then we can continue. Here, in this electronic measurements, right, generally related to the weightage point of view, electrical people gate exam, Instrumentation people, GATE exam it is there, and electrical people, ESC, engineering service also the subject is there. Means those who are online, electrical people, right? GATE as well as ESC, for both examination, the syllabus is there. And for EC people, that is separate. Clear? In this electronic measurements, I have divided this entire thing like this. First, I'll give the introduction. What are the electronic measurements? What are the advantages? What are the disadvantages, etc. I'll be giving corresponding introduction. Right? And after that, the first chapter is analog voltmeters. So what do you mean by analog structure? What do you mean by electronic analog instruments? And after that, we'll be going for digital voltmeters. We'll be going for digital voltmeters. And after that, Q meter, quality factor measurement meter. In the electrical measurements in the bridges chapter, we have seen measurement of quality factor, that is determination of quality factor with the help of bridges. But now we are going to take a device called Q meter. It is a device which is measuring the corresponding quality factor of a given unknown coil, we can say. And the last chapter is somewhat lengthy chapter, CRO, cathode ray oscilloscope. And after that, some miscellaneous topics will be there. I'll be taking that as the safe side point of view. This is the syllabus for both GATE as well as ESC. Right? For electrical people, GATE and ESC. This is the common syllabus. Right. In this, electronics batch students are there. Electronic students only to be here in this class. Mandala Ashwini. Actually, this is electrical branch people, right? Right. This is the branch name for electrical, but the subject name is electronic measurements. This is for electrical people only. Electrical people are having measurement subject. In the two parts are there. One is electrical measurements, other one is electronic measurements. No need to worry. This is the syllabus for electrical students only. No need to worry. Yes, electrical students only. Yes, this is the syllabus available. But the main problem here is, sir, if you are saying that electronic measurements, so this is for electronic students, not like that. Electrical students only. The syllabus is there, electronic measurement. This is second part of measurement. But other people are asking the question again and again. No need to worry about the electrical measurements. It will be taken later. The schedule will be given by the corresponding person. No need to worry. Electrical measurements also will be done. Clear? Right? So this is the total introduction regarding the entire subject. Right? Here I'll be taking some miscellaneous topics. After this entire thing, I'll be taking some miscellaneous topics for safe state point of view. Sometimes you may be getting the questions from out of syllabus like that, etc. will be given. No need to worry. Right. The screen is black only. I'll be using white color and yellow color. No need to worry. Right. Now, here the weightage of this subject is generally, as you know, from the entire measurement, from this entire measurement generally, from entire measurement, generally for electrical people, I'm giving 4 to 5 marks, or sometimes 5 to 6, or sometimes 3 to 4, I told you, right? And from this, we'll be having electrical measurements. And second part is electronic measurements. Electrical measurements and electronic measurements. So combinedly, you are getting 4 to 5 marks. Sometimes 3 plus 2, sometimes 4 plus 2, or sometimes 2 plus 2, etc. will be there. So weightage is 4 to 5 marks from this entire measurement subject. Clear? This is GATE. This is GATE point of view. But if you are coming for ESC, because few people are there, engineering service examination students, ESC, electrical people, ESC, electrical people, the objective, nothing but prelims paper, around 20 questions will be there. 20 questions means we can say 20 into 2, 40 marks, 20 questions we say. In the means that is conventional, we can say that is around 50 marks is the weightage from entire measurement subject. But here we will be taking measurements as a two parts. One is electrical, another one is electronic. That's why first part is done. Now we are starting the second part. But newcomers, no need to worry. I mean, newcomers means newly attending my class, no need to worry. Electrical measurements will be taught later. Schedule will be given by the corresponding person. So no need to worry about anything. Right now, kindly don't ask this question. How many days? How many days? I have not started yet. Kindly, I have not started yet. But compared to electrical measurements, this syllabus is very less. Only 4 chapters. The two, these 2 chapters are little bit small chapters only. Only these 2 are little bit lengthy topics or lengthy chapters, we can say. Not like electrical measurement lengthy syllabus is not there here. Simply only 4 chapters. The two chapters very small, 2 chapters somewhat larger topics. So no need to worry. Clear? But see, strictly speaking, this is your syllabus. According to the GATE or ESC, this is your syllabus. But in order to understand this entire electronic measurements, I would like to give you the introduction part. I would like to give you the introduction because so many days over after completion of measurements, right? Almost 1.5 month, 2 months gap is there. And that to other people, electrical measurements itself is not done. So that's why I'll be taking the introduction of electronic measurements. So what is electronic measurements? What are the advantages? What are the applications, etc. I'm taking. So that you'll be getting some idea. But those who attended my electrical measurements class, this introduction chapter is a revision topic. But those who have not attended my electrical measurements, for them, this is the introduction, means just introduction only. Means just brushing up all the topics. So no need to worry, kindly concentrate. Each and every doubt will be clarified. At the end of the session every day, time will be given for doubts clarification. No need to worry. Clear? Now let us start the topic. Introduction. So what do you mean by electronic measurements? What do you mean by electronic instruments, first of all? Generally, we are having 2 types of instruments. One is electrical and one is electronic. What do you mean by electrical? What do you mean by electronic? Means, as I told you in the first class itself, general categorization is electrical instruments are having less size, strictly speaking, less size. But electronic instruments are having very less size, right? And electrical instruments are having high sensitivity, but electronic instruments will be having, what is it, highest sensitivity or higher sensitivity. So therefore, electrical and electronic instruments, if you are comparing, advantages are more or less almost same, but electronic instruments will be having little bit more advantages. And I gave you one more point. In the electronic instruments, 2 categories will be there. One is analog electronic, another one is digital electronic instruments. Now we are going to take what is analog voltmeter, first chapter, digital voltmeter, second chapter, like that. One by one chapter we are going to take. Clear? So this is the simple idea. Electronic instrument means, what is it? High sensitivity, good resolution, and high accuracy, high speed. All we have taken the introduction of total subject. Yes, now also I'm giving the entire introduction. What is it? Electronic instruments advantages, electronic instruments applications I'm taking. After this entire introduction brush up, we are moving to the first chapter, that is analog voltmeters. Clear? This is the simple idea. Am I not audible properly? Can you let me know? Respond kindly. Am I not audible? So your voice is breaking, few people, perfect few people. Few people are saying that completely audible, but few people are saying that voice is breaking. Okay, right. Okay, right. See here, what are the advantages of electronic instruments and what are the applications of electronic instruments that you are going to see now. So what is that? Kindly concentrate here. Advantages. So in this entire advantages, kindly concentrate on the one by one topic here. More reliable due to use of semiconductor devices. Nothing but in the electrical instruments, almost mechanical construction will be there. Right? Shaft type arrangement, spindle, bearings, springs, etc. will be there. But in the electronic instruments, we'll be having more reliable, we'll be having the more reliability because semiconductor devices will be used. So what is that semiconductor device? The semiconductor device, one of the semiconductor device, diode, etc., etc. Yes, if you are using those type of diodes, yes, we are forming one type of instrument that is called as rectifier type instrument. So automatically semiconductors having more advantages and more reliable nowadays. That's why electronic instruments are also, what is it, more reliable, we can say. First advantage. Second one is weak signals can be detected due to use of amplifiers. But in the electrical instruments, amplifiers, etc. will not be there. Why? Amplifiers are electronic instruments only. That's why, right? By using the amplifiers, we can amplify the signal so that weak signals also can be detected. After detecting the weak signals, to have the proper notation, we can amplify the signal. That is what second advantage. And high sensitivity, because electronic instruments will be responding for smaller values also. If any device is responding for smaller values, then that type of device is called as highly sensitive device. So therefore, high sensitivity. Hence, capable of measuring very small signals. What is the sensitivity, guys? Sensitivity means responding for smaller values. Yes, as it is having high sensitivity, small values or small signals also can be measured properly. And very, very important is loading effect. So what is loading effect? Can anyone? Those who attended my class earlier, what is loading effect? Kindly let me know. What is loading effect? Anyone? What is loading effect? Different answers people are giving means. Come on here. If you are not attended my class, that's okay. But even after attending my class, right? Okay, few people give the correct answer. Right. Nothing but due to internal resistance. Due to internal resistance, whatever the error is happening, whatever the error is taking place, that error is called as loading error. That effect is called as loading effect. And the two electronic voltmeter notation I'm saying loading effect is less. Why the loading effect is less means these are having high internal impedance. These are having high internal impedance. So what is the meaning of high internal impedance? I think, but if the impedance of the voltmeter is very, very high, already we have taken one proof also with the loading effect concept, right? 600 ohm, etc. We have taken one concept and we have proved that voltmeter should be having always high impedance only. Yes, here also, as the electronic instruments are inherently designed with high input impedance, right? The loading effect is less. I think, but the loading error is less, we can say. Loading effect is less, yeah, loading error is less. And they have ability to monitor remote signal also because electronic itself indicates remote operations are possible. Therefore, the ability to monitor remote signals also. So all these are the advantages of electronic instruments, right? And few more. They can monitor, control, record the quantity to be measured. Yes, definitely. Recording system will be there. monitoring system will be there automatically, controlling system. So electronic instruments can perform all the operations, can monitor, can control, and can record the values accordingly. And they have faster response. All I told you, high speed of response. With respect to which one here, compared to electrical instruments, electronic instruments will be having high speed of response or faster response, we can say. That's why they have faster response time on account of very small inertia. Very important, on account of very small inertia. I have given in the basics of measurement only. Electronic instruments are having very small inertia. That's why, what is it? Very less time constant, means those will be responding as quick as possible, as early as possible. Therefore, we can say, yes, faster responses. Faster response will be there on the account of small inertia. That is around millisecond to nanosecond of time. Millisecond to nanoseconds of time. And light in weight, compact in size, all I told you in the starting point only, very small size and very less weight. Power consumption is very less, greater flexibility. So all these are the advantages of electronic instruments. But with respect to all these, kindly don't say electrical instruments are having drawbacks or disadvantages. No, I told you already, electrical instruments are good, electronic instruments are better. Otherwise, electrical instruments are better, electronic instruments are best. In that way, I told you already. But mechanical instruments are ruled out. Mechanical instruments generally we don't prefer nowadays. Electrical instruments we use, whatever the devices we use in machines lab, measurements lab, etc. All those are coming under electrical instrument category. And whatever the devices we use generally in the electronic laboratory, those are coming under electronic instruments. So these are the advantages of electronic instruments. Why I'm taking this entire introduction means just to brush up the entire system. After that, I will start the syllabus. Clear? Okay. Sir, what are the applications of this? What are the applications of this electronic instruments? See, applications are scientific and industrial measurements, obviously, right? As these are having these many advantages, scientific purposes means in the research laboratory also we can use. And nuclear instrumentation, bioinstrumentation means nuclear power plants or nuclear type of industries, for example, nuclear type of power plants, etc. There we are using electronic only. And bioinstrumentation, servo systems, chemical process and power systems, nothing but what not, every practical company or practical, what is it, industry we can say, in almost all industries, electronic instruments are used. But I'm not saying that electrical instruments are not used. No, electrical instruments will be used. At the same time, electronic measurements are also, electronic instruments are also used. And measurement of non-electrical quantities. Actually, this part is not there for you in the gate point of view, but for ESC people, this topic is there in the ESC syllabus. That is third part of the measurement, transducers we can say. Transducers that will be taken later, no need to. Clear? Measurement of non-electrical quantities. Sir, what are those non-electrical quantities? Like here, non-electrical quantities means it may be a force measurement, it may be a pressure measurement, and temperature measurement, and flow measurement, like this, etc. If you want to measure all these also, yes, electronic instruments, electronic measurement procedure can be used. And all these are called as non-electrical measurements. Clear? And detection, electromagnetically produced signals, detection of electromagnetically produced signals such as radio, video, and microwave. So radio, video, microwave itself indicates electronic notation only. Yes, electronic instruments can be used. Right? Yes, one student gave that. Shiv Prasad, like tachometer. Yes, tachometer is used for measurement of speed. Yes, that is one type of electronic devices. And communication fields, space communication, for transmitting and receiving signals. Computers, anyway, computer itself is electronic type of device. And intermediate signal modifying stage. What do you mean by that? Modify means I want to reduce the harmonics. I want to amplify the signal. I want to convert one form into other form, like that. In all those intermediate stages also, electronic instruments will be generally used. So these are the simple advantages and applications of electronic instruments. But strictly speaking, people are asking that, sir, what about the disadvantages? Actually, disadvantages are very less compared to electrical instruments. But every procedure or every process or every system will be having disadvantages. But right now, we don't know any electronic devices in particular. That's why we are going to give the disadvantages for a particular electronic device. Okay, this is the disadvantage. Separately, we are going to give. Universally, compared to electrical instruments, electronic instruments, disadvantages, we cannot list out properly. That's why type to type of the device we have to take and complete construction operation. Then what are the problems we are facing, etc. We are going to take care. That is what the total introduction I wanted to revise. You can take anything. This is the total part before starting the electronic measurements. Are you clear with this simple introduction I gave you? Just brush up for a few people. For other people, just new topic, just introduction I gave you. Is it clear, guys? People are saying that voice is too slow. Just wait for 1 minute. Right, we are checking about the audio connection and it will be rectified. No need to worry. I inform the corresponding person, it will be rectified. Now I'm starting the first topic, that is analog voltmeters. The first chapter, that is analog voltmeters. Right. So what is analog voltmeter? In this analog voltmeter, what are the types of device are there, etc. Everything I'm going to give now. Right. See, in this analog voltmeters are analog electronic instruments. The first, generally the topic available here is rectifier instrument. We are going to take rectifier instrument. Rectifier type instrument. So this is the first topic in this electron. Right now, here, sir, what do you mean by rectifier type instrument? Very, very, very important point here. What is the necessity of rectifier? type instrument and what is a construction related to this entire thing I'm going to give. Kindly concentrate here. Sir, my requirement, kindly concentrate why we are using this device that I'm discussing first. Sir, we are having AC supply first. For example, AC supply is there. Sir, AC means generally we talk about RMS value. So therefore, RMS value. Okay, AC supply, that is RMS value. Okay, happy. But now I would like to measure this AC. Kindly concentrate. I would like to measure this AC with the help of, I would like to measure this AC with the help of a device which is having the linear scale. Sir, out of available all the devices, PMMC, MI, EMMC, electrostatic, etc., which measures the voltage and which is having the linear scale means only one device, that is PMMC. So therefore, I want to measure the AC with the help of linear scale device. So what is the type of device we are having? Linear scale device is nothing but PMMC. But I'm mentioning this point. Those who are not done with the electrical measurements, don't worry. PMMC, how the linear and why the linear scale, everything will be proved. But you take it for granted. So PMMC instrument is linear scale instrument. Okay, happy. Sir, if I connect directly like this, everyone who was on the line, kindly let me know what is its reading. If I connect directly, what is its reading? Come on. Very nice, very nice. Right, okay. Everyone give the correct answer. What is it? Zero voltage. It will show zero. Sir, if it is showing zero, can we say that, sir, this value is perfectly measured by the PMMC instrument? Can we say like that? Yeah, definitely no. So that is the reason why. What we can say now, PMMC cannot be connected directly. Okay. People are saying that, sir, why are you going for PMMC? Why don't you use MI? Okay, if I use MI like this, yes, it measures RMS value. Okay, happy. But what is my requirement? I need to measure this AC. I need to measure this AC with the help of, I need to measure this AC with the help of which device? With the help of linear scale type of device. MI is not linear, so that's why don't go for MI. Our requirement itself is linear scale device must be used. Okay, PMMC. But we cannot connect this PMMC directly because PMMC reads zero when we give AC supply directly. That's why which type of element is to be connected here? One particular electronic structure we need to connect, that is called as rectifier. So therefore, we are going to connect the rectifier structure here. So what is a rectifier structure? So what is a rectifier structure? The rectifier structure here is, right here, I'm using one rectifier here. Now the question here is, sir, what is the type of rectifier? What is the type of rectifier? Means the rectifiers are two types. One is half-wave rectifier and other one is full-wave rectifier. So what is it? We'll be seeing that later. And here it is connected. It is connected here. And this will be connected like this. So what is this device? This device is rectifier. This device is rectifier. Now tell me here, AC is given, that is bidirectional supply. Assume that sinusoidal supply like this. Assume that sinusoidal supply. Clear? Right, sir. Here, this sinusoidal supply, yeah, we can say bidirectional supply is being converted into unidirectional supply. That is what rectifier purpose. So therefore, that unidirectional supply generally we call it as DC. DC. Of course, it is not pure DC, but unidirectional supply. So therefore, which type of output will be there? Here, if it is a half-wave rectifier, output will be like this. Okay. And if it is a full wave rectifier, the output will be like this. Clear? Now tell me, sir, this is only one-sided waveform. This is also only one-sided waveform. As this is one-sided waveform, yes, PMMC measures this value clearly. So therefore, no zero indication. It will show average value of this entire data. Therefore, what we can say, yes, PMMC reads which value? Average value, right? There is no question of corresponding zero indication, etc. Why? This is not bidirectional. If it is a bidirectional, I told you clearly, for positive half cycle, pointer moves forward. For negative half cycle, pointer comes backward. Means forward, backward, forward, backward. It will oscillates around zero. As it is oscillating around zero, we can say it shows zero value. Is it no? Same thing. But here it is, there is no negative value at all, only positive value. Only positive value. Therefore, what we can say? Yes, only positive. We can say yes, PMMC reads some non-zero value according to the corresponding. So this is the total introduction regarding rectifier type instrument. But the problem here is, so what is our unknown value? Everyone, what is our unknown value? RMS value. What is the measured value, or what is the observed value, or what is the obtained value? Average value. Okay, but sir, suppose this average value is 5 amperes for example. This average value is 5 amperes for example. Can I say that, oh, okay, measurement is being done, I RMS supply is 5 amperes? Can we say like that? No. Why? This 5 amperes is, this 5 amperes is which value? Average value. But what we require, this average value is to be converted into RMS value. Sir, how do we convert average value into RMS value? How do we convert average value into RMS value? Anyone? People are still saying that voice is breaking. One second, be online. Right. Any consider here? Sir, What we require here, average value must be converted into RMS value. Few people gave the answer that we have to add which one correspondingly. Which factor? Farm factor. Some people said that root 2, right? Some people said that some other value and 1.11. Few people said that farm factor and few people said that peak factor. But which is correct among all these? Which is correct among all these? Be clear, guys. Root 2, 1.11, farm factor, peak factor, different answers. And one more student gave this inverter as the answer. See, if you want to convert average value into RMS value, are you using or do you use inverter? Inverter means DC to AC, not average value into RMS value. Be clear. DC to AC is called as inversion operation. So you require inverter. But I'm asking average value. PMMC device has shown some value 5 amperes. That 5 amperes is the average value. That 5 amperes average value should be converted into RMS value. Where is the question of inverter here? No way. So kindly be clear with the corresponding question. Clear? Right. Now answer here is by using the farm factor. By using the farm factor. But many people's doubt is, sir, we have studied in the network theory or analog electronics, etc. Farm factor is 1.11. Form factor is 1.11. Therefore, sir, 1.11 is also correct. No, no. Form factor is not 1.11 every time. The form factor depends on the type of rectifier. Therefore, the form factor 1.11 correct, but not always. That depends on the type of rectifier. Now tell me, 1.11 is correct for which type of power factor? For which type of rectifier we can say? Right. 1 second. Sahil Singh, PMMC measures DC. Yes, PMMC measures only DC. Why? And everything will be taken later in the electrical measurements. Those who have not attended, but other people attended, yes, they know this. PMMC measures DC. Okay. Kindly concentrate. This is for full wave. This is for full wave, not half wave, guys. This is for full wave. Right? Mukul Jagtap, you have given half wave. No, yeah, this is for full wave. But my question is, for half wave, what is the corresponding form factor value? Everyone, try to give the answer. Come on. Point 0.5, 0.85, 2.22, pi by 2, 0.693, 0.72. Why these may different answers? 1.11 by 2. Bhavana. 1.57. 0.64. 2.22. Why these made different answers? Did you attend the network theory class? Did you attend the analog class? Right? Then why different answers? Analog over sir. Then okay, in the AS Academy network theory is not done, that's okay. But generally in your BTech at least this is done, right? But to electrical people, form factor is very important. Form factor plays a crucial role. Come on. Right, be clear. Few people are giving that 1.57. Few people are giving that 2.22. Be clear. These two are correct. But here you need to understand one key point. Kindly concentrate here. Here, be clear, guys. The half wave rectifier you're talking or half wave rectifier type instrument you're talking, that is very, very, very important. So that's why be clear with the terminology. Kindly concentrate. You might have studied this portion in the analog electronics subject. Only rectifier. But our topic is not only rectifier. Our topic is rectifier type instrument. So that's why kindly concentrate here. Our topic is rectifier type instrument means this entire thing. This entire thing is rectifier type instrument. Sir, what is the difference between these two? What is the difference between these two means? Rectifier means you are taking the output of rectifier just like that. But rectifier type instrument means you are giving the output of the rectifier to the PMMC instrument. So that's why you need to concentrate with the corresponding terminology. Which type of thing you are taking? Which type of thing you are taking? That is very, very, very important. What is it? Rectifier is the topic you studied in analog electronics. Rectifier type instrument is a topic we are studying in our measurement. So that's why rectifier is different. Rectifier type instrument is different. Rectifier means only this one you're taking. Rectifier means only this one you're taking. But rectifier type instrument means rectifier plus PMMC combination. So what is the difference? I'm going to discuss clearly. So that's why whether it will be 1.57 or 2.22 or 1.11 by 2, etc. What will be there? We are going to see in detail. Clear? So that's why simply what you have to write, concentrate here. Sir, AC supply is given. That is generally RMS value is given. Right? This is given to which device? Rectifier. This is given to rectifier. This rectifier gives which value? DC value. Clear? This DC is given to PMMC instrument. Okay. This PMMC gives which value? Average value. Sir, this average value must be converted into RMS value. This average value must be converted into RMS value, right? Then what we require? Form factor we require. Kindly don't say 1.11, yeah 2.22, yeah 1.57. Universally now itself don't say. After my explanation, you will get clarity where we have to use 1.11, where we have to use 1.57, where we have to use 2.22, etc., etc. Then you will get the clarity. Then you can use based on the condition. Okay, so that's why here I'm writing just a form factor. I'm not writing the form factor value blindly because that depends on the type of rectifier. The two, not only rectifier on the instrument also, that is rectifier plus instrument combination, it will be different. So that should be clear. So form factor is equal to what is the formula? RMS value by average value. RMS value by average value. So from this, what we can write? Average value is equal to form factor into RMS value. Average value is equal to form factor into RMS value. Clear? Right, sir. Very, very important point. Sir, in this entire thing, everyone answer this. In this entire thing, which is the measured value? Come on, guys. Which is the measured value? Average value is the measured value. RMS value is the measured value. Come on, which value is measured value? Yes, average value is the measured value. Come on. Come on, guys. Average value is measured value. Okay, very good, very good, very good. Yes, few people are observing clearly. Kindly concentrate. This is not correct. People are not observing, directly taking. What is this? Average value is equal to RMS value by form factor. I have given intentionally different multiplication division wrong. Only few people pointed out this, but other people taken for granted, right? Yes, very good. Here, actually, like this will be there. What is it? RMS value is equal to RMS value is equal to form factor into average. Clear? Now come back. Yes, many people told that. Okay, okay, right. Very good. Vikrant, no problem. Sometimes I will do like this so that I can understand whether you're correcting or you're observing or not. No need. I'll correct it. Anyway, I'll correct it. Right? Means if you are pointing out this one, you are concentrating. That's what the simple idea. Other people also. Right. Sir, which is the measured value? Average. So that I'm writing like this. Sir, this is measured value. Okay. And RMS value is true value. So true value is equal to measured value into something. So what we can say now? This factor we can write as correction factor. And in the first class of error analysis, during the first class of error analysis, I have given that what is it? Measured value is being corrected and equated to true value. So therefore, with this entire discussion, in the rectifier type instrument, what is the correction factor value? Come on, guys. In the rectifier type instrument, what is the correction factor value? Means don't give the value, give the name. That is form factor. The correction factor value is just form factor. What is the value? We are going to see in detail one by one later. Here, this is the first objective question in the GATE model. Right? Form factor is the correction factor. Yes, measured value is being corrected, equated to true value is correction factor is form factor. Therefore, in this entire rectifier type instruments chapter, right, very important factor is form factor only. That's why we need to concentrate more on the form factor. Clear? Okay. But we cannot give the form factor value directly like 2.3 or 5.6 or 1 point like that. We cannot give. That depends on the type of rectifier. So that's why in this rectifier type instruments, there are two types. One is half wave rectifier. Kindly concentrate. If you stop here, this is your analog electronics. This looks very silly, but this very important point, confusing point also. What is it? If you stop here, just half wave rectifier, it will be your analog electronics. Yeah, network theory subject. But our topic is half wave rectifier type instrument. Half wave rectifier type instrument. Then we can say, yes, correspondingly, this is our measurement topic. But what is the difference between half wave rectifier and half wave rectifier type instrument? Everything will be given clearly known each other. Right? Next. Second one, as usual. Full wave rectifier type instrument. Full wave rectifier type instrument. Clear? These are the two types available, half wave rectifier type and full wave rectifier type instrument. Now let us start the first topic, half wave rectifier type instrument. Can you be clear? Half wave rectifier type instrument. So first of all, what do you mean by half wave rectifier? What do you mean by half wave rectifier? How will be the input and how will be the output? Let us see that first. Here I am taking y-axis, and here x-axis, and here one more x-axis. Kindly concentrate here. So here sinusoidal waveform I'm taking. One cycle waveform I'm taking here. Sinusoidal waveform. Like that, one more cycle. Two cycles of structure I'm showing. Okay, this is VI. What is VI? Rectifier input, right? And this anyway omega t 0, pi, 2 pi, 3 pi, 4 pi. Okay, in the same way, like this. Right now, sir, what is the output of the rectifier? V naught, output of the rectifier. I have given clearly here. This is DC. So therefore, I'm clearly mentioning this is VI and this is V naught and clear. Okay, sir. Here, this is V naught. Half a rectifier means only half a cycle is being conducted, other half cycle is not being conducted at all. Still, people are saying the same problem. 1 second, kindly be online. Right. See, here the output will be only half a cycle conduction. So therefore here this is being conducted and half cycle not conducted. Again conducted, not conducting here. Right. This is output of the rectifier. Clear? Again, this is 0. This is pi, 2 pi, 3 pi, 4 pi. Now, very important point here is, if you understand this point, right. Can you consider here, sir? What is the corresponding explanation? Corresponding crucial point here is, can you consider, guys? Among these two, which is the input of the entire rectifier type instrument means VI. So therefore, where we have to find out the VRMS here. Therefore, VRMS is equal to Vm by root 2. Clear? Okay, sir. Among these two, which is the output of the rectifier? V0. Now, second question. Among these two, which is given to PMMC instrument? Among these two, which is given to PMMC means V0 is given to PMMC. Therefore, PMMC measures average value of this or average value of this means automatically average value of this only. PMMC measures average value of only this device. So therefore, we need to find out V average of this. So what is the V average of this? Everyone knows that half a cycle is conducting, or a oral cycle is being taken Vm by pi. Vm by pi. Clear? Right. Now the question here is, sir, everyone concept very, very important. In your analog electronics and in my measurement, what is the difference? Both concepts are correct. Both concepts are valid everywhere, but based on their condition. Means in the analog electronics, rectifier type output form factor you take. Rectifier output form factor means this is the rectifier output. So rectifier output form factor means rectifier output average value, rectifier output RMS value. Both must be taken. Rectifier type, rectifier output average value, rectifier output RMS value. Then we can say, sir, rectifier form factor or rectifier output form factor that you take in the analog electronic subject or network theory subject. But in our case, rectifier output we are not dealing. Rectifier output is given to PMMC. PMMC reading is to be converted into main RMS value. That's why. Now tell me, RMS value of this is to be determined or RMS value of this is to be used. Which is to be used? RMS value of this to be used or RMS value of this to be used? Can you let me know? RMS value of which must be used? Everyone should respond this question, then you can understand difference between analog as well as corresponding measurement difference in this particular thing. RMS value of which one? Okay, few people, yes, yes, I know, because many people are giving the same answer every time. Right. I got the answer from many people. RMS value of VI, RMS value of V naught equally given. This is what the problem. See, if I take VRMS, VRMS is Vm by 2. If I find out form factor, if I found out form factor, you'll be getting pi by 2. That is 1.57. Now tell me, sir, if I say this is the form factor of this device, how can I say this? So now tell me, in this entire thing, did we use any PMMC application here? Did we use any PMMC application here? No. Average value of this, RMS value of this, and relation between these two means we have taken only output of the rectifier. We have taken only rectifier output. But what we require? Rectifier type instrument we require. Rectifier type instrument form factor we require. That's why go back here. Sir, this is the average value. What is it? This is rectifier output. Average value is there. Now tell me, this average value converting this RMS value or converting this RMS value? Can you let me know? Converting into which RMS value? This average value is being converted into its RMS value or main input RMS value means main input RMS value, but not rectifier output RMS. Are you able to understand? If you understand this key point, you can understand the difference between rectifier, rectifier type instrument. Can you let me know? Are you clear? Right. Come on, guys. No. Yes, I will repeat. Imtiaz and some other person is asking that repeat this sentence. I will repeat. No need to worry. But those who are done, is it clear or not? Pratyusha will repeat it. No problem. Yes, Sai Charan Reddy, correct. Yes, Priya, Raj, everyone is saying that. Right. See, clear. So simple point. Average value of this is being converted into RMS value of this or RMS value of this. Average value of output is being converted into RMS value of output of the rectifier or RMS value of input of the rectifier means input of the rectifier only. So that's why I give this flow chart based concept. AC RMS rectifier converting that into DC. DC is being converted in given to PMMC, given to average. Okay, sir, given average. Now tell me this average value is being converted into its RMS value or main input RMS value means main input RMS value only, but not this RMS value. Suppose if you take this average value converted into this RMS value, then that is called as rectifier output form factor. What is rectifier output form factor? Concentrate. Rectifier output form factor is here. Rectifier output form factor here is rectifier output RMS value, rectifier output average value. If I take these two, what is it? Average value of this, RMS value of this only. But we don't want this RMS value. We want this RMS value. That's why lot of difference is there between rectifier output form factor, rectifier instrument form factor. Are you clear at least now? Clear, guys? Yes, very good. Right. Kindly, Navin Sai, Allah Navin Sai. That means we need to multiply with respect to form factor of V input. Don't say form factor of V input. Say form factor of rectified type instrument because one input does not have form factor. Total system. So that's why rectified type instrument form factor. If you understand this point, my next continuation topic is very simple mathematical topic. Clear, guys? Right now I'm repeating this point again to continue my topic. If I find VRMS is equal to, you'll be getting VM by 2. If I say this has a form factor, yes, 1.57. This is the form factor of rectifier output, not the rectifier type instrument, not the rectifier type instrument. So that's why our topic is rectifier type instrument. That's why input RMS, output average. This must be converted into this RMS value. So that's why I'm writing here clearly from this. Sir, V average is equal to, in the place of VM, we can write root 2 times of VRMS. Root 2 times of VRMS by pi. So root 2 by pi, we are going to get 0.45 times of VRMS. So V average is equal to 0.45 times of VRMS. Clear? Right. Now let us proceed the entire discussion. Right. So why don't you use earphones, please? See, except you, everyone is saying that the voice is clear only. Right. Kindly concentrate here. I have spoken with the person and he's saying that kindly let them check from their side. Kindly check from your side once regarding earphone checking, etc., etc. Kindly check that. If the problem is continued, I'll let you know. I have spoken with the corresponding person just now. He's saying that problem is not from our side, from their side. Only he is saying like that. Right? Okay, come back. Sir, V average is equal to, what is VM? VM equal to root 2 times of VRMS. So root 2 by pi, if you're simplifying this, you are going to get 0.45 times of VRMS. So average value is being converted into RMS value. The two, this RMS value is main input RMS value, not the rectifier output RMS value. So no problem at all. Clear? Right. Now, let us proceed. Sir, here, what is the value here? V average is equal to, V average is equal to 0.45 times of VRMS. Right? Sir, what we can write now? 0.45 can be written as 1 by 2.22. Calculator, if you calculate it, 1 by 2.22 is 0.45 times of VRMS. This is equal to V average. Okay. Now, therefore, V average into 2.22 is equal to VRMS. Right. So, what is this value now? This value is form factor. Therefore, here we can write form factor is equal to VRMS by V average is equal to 2.22. This is the value of form factor in rectifier. That is which one? Half wave rectifier type instrument. Kindly, I'm requesting everyone, don't say 2.22 is the form factor in half wave rectifier. No, half wave rectifier instrument you have to say. Otherwise, it looks like half wave rectifier output form factor is 2.2. No, output of the rectifier form factor is 1.57. But our topic is not only rectifier output is being converted into rectifier input. Average value is being converted into RMS. That's why 2.22 is the answer. Clear? Now, sir, V average measured value. Okay, VRMS true value, and whatever the factor is there, that is correction factor. So therefore, what we can say, correction factor is equal to form factor is equal to 2.22. In which device? Half wave rectifier type instrument. Clear? Sunita V Desai, kindly don't say that for this rectifier, no, for this rectifier type instrument, kindly I'm requesting, rectifier is different from rectifier type instrument. I told you, yes, that's why kindly use rectifier type instrument. Your thought is correct, but only one word, rectifier type instrument is 2.2, which one? Half wave. Clear? Okay. After this, I'm going to the construction side. This is also very, very important. Based on this, especially for us, electrical people, previous questions were there. Right? Haripriya Boda. Sir, what are measured in true values? Says, I think you have not attended the class. Whatever the device shown value is there, that is called as measured value. Whatever the main required value is there, that is called as true value. This is, that's why I give the brush up also. Measured value, observed value, unknown value, true value. That is what? Measured and true value. Clear? Clear, guys? Right. Now, after this entire analysis, what the manufacturers are doing practically means very, very, very important. Kindly concentrate here. Whatever the PMMC instrument is available, right? This is the PMMC instrument. This is the PMMC instrument. This is 0, some scale will be there here, some value, right? This is full scale value. Okay, 0 to full scale value. Here pointer will be there. Kindly concentrate. This is PMMC instrument. This is PMMC instrument. Okay, right. Now, sir, after this entire analysis, what modification is being done by the manufacturer based on that? Based on that, we are having so many questions in the competitive examinations. Clear? Right? So therefore, kindly concentrate here. This is 0 to full scale value. This scale is average scale. Why? PMMC instrument is generally having the scale average scale. PMC instrument is having average scale because it measures average value, therefore average scale. So that's why after this, what they do, manufacturers make one more scale like this, and here 0 as it is 0. Suppose here x is there, x into what is the value here? Average value must be corrected, means multiplied and equated to RMS. No, actually this must be done practically by us, but manufacturers are doing themselves and keeping the value inside the instrument directly. Therefore, what they do here, average value into 2.22 is equal to RMS value. Average value into 2.22 is equal to RMS value. Therefore, this value into 2.22, this value into 2.2, like that, every value into 2.22, they are going to keep the scale like this. And after that, strictly speaking, this will be erased. This will be erased. Now tell me, this is the PMMC instrument or not? Yes, this is still PMMC instrument only. But in this PMMC instrument, the scale is RMS scale. The scale is RMS scale or average scale. Everyone, RMS scale. So that's why now we have to say this device is called as which device? Rectifier type PMMC, not the just PMMC. Just PMMC means whatever we have taken so far, that is called as just PMMC normal scale. But now average values, whatever were there so far, multiplied by 2.22. Multiplied means here 1, here 1.1, here 2, 2.22, here 2.5, like that. All values will be multiplied by the corresponding, 2.22 multiplication, 2.22. 2 into means 4.4, like that will be there. Therefore, the calibrated scale will be there. This procedure is called as scale calibration. Which scale? Average scale calibrated into RMS scale. Then that type of PMMC is called as rectifier type PMMC. But be clear, this scale will not be given in the practical device. But for a clarity purpose, I need to show this so that you can understand that average scale was there, multiplied by form factor and made into RMS. That's why we can say here average scale is calibrated into average scale calibrated into which scale? RMS scale. Average scale is calibrated into RMS scale. Clear? So therefore, rectifier type instruments are the instruments in which average scale is being calibrated into RMS value. Clear? Now tell me here, are you changing the scale nature? Scale is linear. Still, scale is linear only. Here, scale is linear only. Here, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Like that, linear displacement, uniform displacement is there. Here also, this value, here to here, here to here. Distance is uniform. Value is also uniform change. That's why scale is still linear only. You are not changing the scale. If you are changing the scale, what is the meaning? Here so many values, or here so many values, like that will be, that it becomes non-linear scale. But here PMMC scale is same. Only we are changing values from average value into RMS value by multiplying with 2.22. That's why the scale is still linear or becoming non-linear. Still linear only. Clear, Manish Kumar? Is it clear? Yes, it's now measuring RMS in linear scale. Very good, very good. Correct. Clear? So this is a total discussion regarding half-wave rectifier type instrument. Right? And one student is saying that it's a small, can you speed up little? It took too slow. Yes, yes. See, Navin Sai, you might have attended the electrical measurements earlier, or you might be so much of talented, but I need to take care of each and every student. And many people not attended my electrical measurements class. But so many places I need to say, yes, we have seen this in the electrical measurements, but I need to revise that entire part. That's why, as this is the starting point, I'm going with corresponding speed only. No need to worry. Wherever I need to speed up, I will speed up. No need to worry. Right? Yes, yes. That's why many people did not. If I want to take that, yeah, you studied this in PMMC, that is electrical instrument, my topic is over. But everyone should understand. That's why I'm repeating the corresponding things. Can you, Navin Sai? Can you have the patience and listen this again? It will be like a revision. Clear? Right. So this is a total discussion. Now tell me, this is just PMMC or rectifier type PMMC means rectifier type PMMC. This is not just PMMC. Clear? Any confusion? Can you let me know? For every topic, and many people know that for every topic I'll be asking, is it clear or not? So if it is clear, kindly let me know. Right. Right now, so after this, let us have some mathematics here. So what is that mathematics? Sir, here half-wave rectifier type waveform we have taken. Okay, well and good. Now I'm taking half-wave rectifier circuit so that we can have corresponding mathematics. Sir, this is AC RMS value, right? And here half-wave rectifier means single diode will be there. I hope everyone knows this. Everyone know about this. And here we will be having PMMC instrument. This is PMMC instrument. This portion is rectifier. So therefore, RMS value, rectifier, and PMMC device, 3 stages. But sir, here always the moment we give the supply, right? The PMMC instrument is used here. The PMMC instrument has its own scale. PMMC instrument has its own scale. Right? PMMC instrument is nothing but simply its own scale, corresponding capacity. So therefore, the moment we give the supply directly like this, right, to avoid the damaging of PMMC, we are using, or we have to use some resistance. This is called as resistance, or we simply called as multiplier, or this is for protection of PMMC. Means this resistor limits the current such that the current flowing will not be exceeding the corresponding scale value or corresponding capacitor of this instrument. That's why this RS is called as current limiting resistor, multiplier resistance used for protection of PMMC instrument from excess current flow. Right? If it is not there, there is a chance of flowing excess current sometime. That's why RS value must be chosen such that the PMMC instrument must be operated under safe conditions. Suppose 0 to 3 ampere we are using. So 0 to 3 ampere, so and so supply we are connecting. Therefore, the current will be flowing 4 ampere. For example, it will be damaged. That's why by adding this resistance, this 4 will be reduced to 3. So therefore, 3 is maximum flowing, the entire circuit will be safe. So that's why the RS value is to be determined, is to be set such that the PMMC instrument will not and should not get damaged. Clear? One thing. And one more student, one doubt is asking, Murali, Sir, PMMC instrument is electrical instrument. No. Why are you using the electronic? See, I am not saying that this is electronic instrument. No, this is electronic instrument. So that's why I told you electrical instruments don't use, electrical instruments are not used in the electronic laboratory. So we cannot say. That's why I told you before starting in the introduction. I told you what is that electrical instruments are used everywhere, but in order to get better performance, then we are going to use electronic. Yes, electronic device combination with our electric. That is common. But I'm still saying that this combinedly called as electronic. Why? When electronic device is there, automatically electronic instrument only we have to say. Clear? And why bow down? Sir, this is diodes are rectifier. It is not rectifier. I did not say rectifier. I said only diode. But you forgotten. I think half wave rectifier means single diode. Diode acts as a rectifier. Why? For half wave, it is conducting. For next half cycle, it will not conduct. Means which action? Rectifier action only. Clear? Rectifier action only. And Mukul, right? Mukul, he's asking, where do we use rectified type PMC? That's why I told you clearly, first only, wherever I want to measure AC RMS value with respect to the linear scale device, in those type of applications, rectified type instrument will be there. Clear? Right. Ram Deni Sairaj. Yes, I'm coming to that only. Let me explain. I'm coming to your question. Clear, guys? Right. So diode has its own resistance RD. Meter has its own resistance RM. Now tell me, guys, this RS value is used. This RS value is placed in the circuit. This RS value is placed in the circuit to protect the PMMC, means to have the IFSD value, right? The current should not exceed the IFSD of PMMC such that the RS is to be determined. That's what our topic. So therefore, our mathematical explanation is related to what is it? RS calculation. RS calculation. Right? Why about no need to don't say sorry. I will answer your doubts. No problem. You can verify. No problem. Sorry, sir, I got confused. No problem. It is not thyristor, diode. Okay, right, sir. Here, sir, what is the I average formula? General formula. I average formula is V average by R total. V average by R total. Clear? Right, sir. What is V average in this half wave rectifier? Kindly go back. V average is, what is it? 0.45 times of VRMS. Oh, 0.45 times of VRMS by. So what is the R total in the entire circuit? RS, RD, RM. Three resistors are there. So therefore, RS plus RD plus Rm. So this is the I average value. Very popular question in the GATE paper for electrical students. Find out the current. Find out the current in the corresponding structure. I average equal to 0.45, etc. But what is our discussion? This RS value is to be determined to have the safe operation of the structure. To have the safe operation of the structure. Clear? Right. Now let us take. Kindly concentrate. Here I'm taking two, right? Otherwise, RS value to have IFSD. RS value to have IFSD. What is the meaning of this? One question. People are asking this doubt even after the class because they are not, this is not you people generally. Here, sir, why you are finding RS value? Again, they are asking. Sir, why RS value only for IFSD? Again and again, they are asking. That's why already I have repeated that point many a times. RS value is chosen such that the current will be in the limit. The current will be under the limit so that the current will not be exceeding its full scale deflection. People are asking IFSD means I full scale deflection. Full scale deflection. Clear? IFSD, I full scale deflection. Clear? Right, sir. Here now, RS value to have IFSD. Therefore, this average value means measured by the PMMC only. Therefore, that average value must be taken as IFSD. Okay, that's what our limit. So therefore, IFSD is equal to 0.45 times of PRMS by RS plus RD plus RM. RS plus RD plus RM. Clear? Right, sir. Here, from this entire thing, RS plus RD plus RL is equal to 1 by IFSD into 0.45 times of VRMS. 0.45 times of VRMS. Clear? Now tell me, sir, what is IFSD? What is 1 by IFSD? What is 1 by IFSD? That is one question. Again, people are saying that, sir, I average becomes IFSD. How? You are not understanding the point. Our target is to find out the RS value to get maximum current. Maximum current means what? IFSD. You are missing again the point here. See, simple logic here. Simple logic. Here, I'm not keeping this. I'm not keeping this. Kindly concentrate. Right? Its value is 0 to 3 ampere, for example. For example, I'm not using this, some value is given. If some value is given, then the current flowing through this will be 4 ampere. Right? 4 ampere is coming here, 4 ampere will damage the PMC. Okay, that is the reason why what we are doing now, we are placing one resistance. Then the current flowing through this will be, for example, 3 ampere. What is its range? 0 to 3. Now tell me, whatever the value shown by the device is average, and that average value must be maximum, such that we need to find out the RS value. That's why be clear with the terminology. I am not taking I average as IFSD blindly. No. After writing this heading only, I am taking I average as IFSD. Because our target is to find out RS value to have maximum safe current. Maximum safe current. Clear? Right. Many people give the answer. Right. Gurukonda Satish. Very good question, but be clear with the network theory. Being an electrical student, kindly more clarity should be there with series circuit. Sir, in series current is same. How IFSD reduce? IFSD will not reduce. What we are doing, that only I told you. This is already defined. To limit that current, resistance is to be added. To limit that current, resistance is to be added. For your clarity purpose, I am taking one circuit. Here 100 volt, right? Here 5 ohm, 5 ohm. What is the current in the circuit? 100 by 10, so 10 ampere. But I want to have only 5 ampere current. I want to have only 5 ampere because I'm using one device that IFSD is 5 amperes only. If I give the supply directly, how much is flowing? 10, but its capacity is 5. It will be damaged. It will be damaged. That is the reason why what we have to add here, we are adding some 10 ohm resistance. Then 10 plus 5, 20, 100 by 20, 5 ampere. Are you clear? Gurukonda Satish? Clear, guys? Nice. Okay. Right. So therefore, we are not changing during the operation. While designing only, that must be designed, that must be selected. Okay, right. Sir, what is 1 by IFSD? Everyone knows that sensitivity. Other people, that is new for this entire measurement, take it for granted. Sensitivity topic, I will explain formula. But sensitivity definition I gave you. Responding for smaller values, etc. I gave you. But sensitivity, other formula is there. That is 1 by IFSD. Okay, into 0.45 times of VRMS. Don't worry, I'm writing here. Since, right, S is equal to 1 by IFSD. Okay, now tell me, sir, this is DC sensitivity, yeah, AC sensitivity. Is it DC sensitivity or AC sensitivity? Come on. Is it DC sensitivity or AC sensitivity? Come on. Yes, this is called as DC sensitivity. Sir, why? Means this sensitivity we are writing here. This is IFSD. Sir, what is IFSD? I average. What is I average? I average is nothing but shown by the PMMC. Shown by the PMMC, which is given? DC is given here. DC is given. Therefore, this sensitivity is called as sensitivity DC. So therefore, I'm writing DC sensitivity. Right? In the electrical measurements, DC, AC sensitivity are not taken. Only sensitivity. Now we are elaborating. So therefore, this sensitivity is called as DC sensitivity. Okay. Right. Now, therefore, what I can write now? RS. I'm bringing these to other side. RES is equal to SDC 0.45 times of VRMS minus RD minus RM. Clear? So this is the final value of RS to have the corresponding full scale deflection. If you are keeping this value in that structure, in that circuit, or in that instrument, we can say that current will not be exceeding the limit. Thereby, the operation will be safe. The operation will be safe. That's what the point. Clear? Right. Or one more formula I'm giving. So what is that formula? Sir, RES is equal to SDC into 0.45. I'm writing SAC. How? I'll prove it. Into VRMS minus RD minus RM. This is one more formula. But you're having doubt, genuine, that is where SAC is equal to 0.45 times of SDC. This combination I've written as SAC. So therefore, SAC is equal to 0.45 times of SDC. Sir, how can you say this is correct? Let us take. Sir, sensitivity 1 by IFSD. Right? Sensitivity 1 by IFSD. But this is DC sensitivity, means average. This is AC. AC means RMS. So therefore, RMS. 0.45, I am writing as 2.22. Now tell me, therefore, IRMS is equal to 2.22 into I average. Clear? So therefore, RMS value is equal to 2.22 into average. Yes, that is what our topic. RMS value is equal to 2.22 into average. Therefore, we can say that here SAC is equal to 0.45 times of SDC. So this is the complete discussion regarding entire half rectifier type instrument from the basics to the entire final value. Clear, guys? Any more doubts? Can you let me know? Right. Priyavat Raj, yes, RS value will be taken related to a particular voltage. That's why I have taken here for a given voltage. Yes, how much resistance must be added? So for a given voltage. Is it clear, guys? Everything will be given as the PDF to you. No need to worry about the notes. And people are asking that 19F, 20F, 21. No need to worry. You follow me continuously. When is the break, sir? Every 2 hours I'll give the break. For every 2 hours I'll give the break. No need to worry. Clear? Right. So this is the total discussion regarding which one? Half-wave rectifier type instrument. Right. Now, if you understand this, the next topic is very, very, very simple. Full-wave rectifier. Very simple. The second part. Full-wave rectifier type instrument. Full-wave rectifier type instrument. Right now, what is it? Full-wave rectifier. Be clear. I'm drawing the diagram first. Then we can proceed for the entire topic. Here, sir, AC supply. AC supply, that generally we can say RMS supply. Okay, what is this? This is VI. Right now, here full wave rectifier means you studied in the analog electronics. There are two types of full wave rectifiers. One is bridge rectifier. Other one is which one? Center tap rectifier, but which is very popular? Bridge rectifier. So therefore, in the introduction only, I'll give you full wave, nothing but full wave bridge type of rectifier type instrument. Okay, right? So therefore, here, what is that? Bridge rectifier. I'm taking one bridge structure here, right? Like this. Now here, one diode. Here, one more diode. Like this, right? And here we are connecting PMMC instrument like this. So this is full wave bridge rectifier. So in this also, to protect the current or sorry, to protect the device or to limit the current, definitely we need to use one resistance, right? Yes, that resistance I'm showing here. This is some RS. What is its purpose? RS purpose is always to limit the current so that the PMMC instrument will be operated under safe operating conditions. Clear? Right. Now, sir, how will be the waveform? Kindly concentrate. I'm going to ask you the same questions for revision point of view. Kindly answer. Sir, here, axis I'm taking, x-axis, that is input, and here, one more x-axis input. This is output. Right? Sir, this is output. Now, concentrate here. This is VI. This is V naught. Right? Here. Like this, one cycle, 2 cycles I'm showing. Input. Sine wave, right? And output will be, right? Can you tell me? It will be conducting For both half cycles or only one half cycle here? Both half cycles. Why? Check it here. Sir, Vi is there. It is anyway. Sinusoidal waveform is there. Okay, right. Input is coming here like this. Positive half cycle. It will be conducting, flowing like this, conducting, coming over here. So that is what half cycle conducting. But for negative half cycle means generally we come in the reverse way. Negative half cycle, right? It will be conducting like this, and path will be completed. So therefore, what we can say, for first half cycle, two diodes are conducting. For next half cycle, other two diodes are conducting. First half cycle, this diode D1, this diode D2 will be conducting. For next half cycle, D3, D4 will be conducting. Okay. Yes. First half cycle is being conducted. Yes, waveform. Second half cycle is also conducted. Third half cycle like this. Fourth half cycle like this. Continuation happen. Okay. Right now, same question. So among these two, which is given to rectifier? Which is given to rectifier? Among these two, which is given to rectifier? Can you let me know? Which is given to rectifier? Right? Input of the nothing but Vi we can say. This is given to rectifier. Yes, Vi. Vikrant, kindly check it. Rectifier I'm asking. Which is given to rectifier? What is it? Vi. Therefore, VRMS we have to take. Why? Our main unknown is this one, VRMS. What is VRMS? Vm by root. Sir, which is the rectifier output? V0. Which is given to PMMC? V0. PMMC measures the average value of which one? V0 only. Therefore, we have to take here V average is equal to which value? 2 Vm by pi. I'm repeating the same point. Sir, RMS value of this must be considered. RMS value of this must be considered means RMS value of input only is to be considered, because our topic is not just the rectifier. Our topic is rectifier type instrument. So therefore, this should be converted into 2 by pi Vm, nothing but root 2 times of VRMS. Root 2 times of VRMS. So 2 root 2 by pi, you'll be getting 0.9 times of VRMS. 0.9 times of VRMS. Clear? Right. Now, sir, what we can write now? V average is equal to 0.9 times of VRMS. Clear? Right, sir. Here from this, form factor is equal to, what is it? RMS value by average value. What is it? RMS value by average value. 1 by 0.9. That is equal to 1.1. Now tell me, 1.11 is the form factor everywhere, or only under the full cycle mode? Is only under the full wave mode. That's why 1.11 for full wave rectifier. Okay. And second point, sir, V average is equal to 0.9 times of VRMS. Okay. So what is V average? V average value is the value shown by the device. Shown by the device. So therefore, what we can say? Measure. VRMS is the value which is given to the entire device, which is unknown. So therefore, true value. Clear? Right? So therefore, here 0.9 is there. 0.9 is there. So AM into what is it? 1 by 0.9 is equal to 80. Therefore, AM into 1.11 is equal to 80. Therefore, what we can say now? Therefore, correction factor is equal to form factor is equal to 1.1. There 2.22, here 1.1. Ashish Raj. Ashish Raj, you have given wrong. What is wrong? Ashish Raj? Come on. No, no. Point 10 is not wrong. Point 10 is that is factor only. But here, yes, this is with respect to full way rectifier. 1.1 by point 10 is 1.11. Now, after that same discussion, sir, manufacturer, what does he do? Simply, they will take instrument. Same concept, they will take instrument. In the instrument, which scale is there? Average scale is there. Which scale? Average scale. Average scale means PMMC generally differ average notation. Like this, some scale will be there according to its full scale value. This is 0. This is full scale value. Okay. And here, pointer. Okay. Now tell me, what is the correction factor in this device? The correction factor is 1.11. Therefore, they will be making one more scale. Here, 0 as it is. X into 1.11. Y into Y, like that. All values will be multiplied. All values will be multiplied with 1.11. Therefore, average value into 1.11 is equal to RMS value. In the earlier discussion, we have taken average value into 2.2. That is for half wave rectifier type instrument. Here, this is for full wave. Now we can say this as rectifier type instrument. Rectifier type instrument. Right? Here also what we can say, average scale is being calibrated into RMS scale. Average scale is being calibrated into RMS scale. Clear? So therefore what we can write, average scale is calibrated into RMS scale. That's why rectifier type instruments are having the scale for RMS, but average scale is being converted into or calibrated into RMS scale. Clear, guys? Right. If any doubt is there, kindly let me know. Okay, no problem. I can write rectifier type PMMC also. Akshay, right? We can write no problem. Rectifier type PMMC. Instrument itself indicate PMMC only will be used. Right. All I told you, Pratyusha, very good question. Kindly concentrate. Generally, this will not be shown. All I told you, this will not be available. Only they will say rectifier type PMMC only they will say. But for your clarity purpose, I'm maintaining this entire scale. Suppose if I erase this, right? After few days, if you study this, you will think like only this scale is directly present, but this scale is not directly present. This scale is being converted into RMS. So that's why practically only one scale generally, but idea purpose I'm keeping both because what was there and how the modification was done, that you have to understand. Clear? Any more confusions? Right now, very important point here is concentrate. Now, it's a very important point. As two types of rectifier type instruments are done, I'm taking this point. First of all, rectifier type instruments are dash indicating and dash responding. Very popular question. That is first point. Rectifier type instruments. Rectifier type instrument indicates rectifier plus PMMC, no doubt. Right? Rectifier type instruments are right dash responding dash indicating instruments. Now, everyone, what is answer for this? See, Rohit and some other people are asking the same question. Here, half wave rectifier type instrument separate, full wave rectifier type instrument separate. Right? Don't think like in PMMs only half wave rectifier scale, full wave rectifier scale will not be there. Both are differently constructed. Both are differently done. No need to worry. Right? Half wave separate device, full wave also separate device. And Simha Shiva Prasad. So in both rectifier type instrument is written half. Yes, definitely half or full they will mention. Even though if that is not mentioned, what is to be taken, I'll tell you when I start the questions. No need to worry. Right? Okay, answer this question. See, first of all, very important point here is, are you changing the PMMC internal construction? No, we are not changing the PMMC internal construction. So PMMC internal construction is same. So therefore, PMMC is which type of device? Average measuring device, average responding device we can say. Therefore, what we can say, in the PMMC instrument, construction is not changed. Therefore, the PMMC structure always responds for average. So therefore, average responding. But finally, it is indicating which value? RMS value. Therefore, RMS indicating average response. Sir, why average responding means PMMC construction is not changed, only scale. That's why I give this point clearly. Average scale is calibrated into RMS, but internal structure, everything is same. We have just multiplied with the corresponding value. So that is the reason why average respond. Respond is for average only. Why? PMMC. Because PMMC responds for average every time. But showing which value, the scale will not be there. Therefore, directly it is showing RMS. Therefore, this device is indicating the RMS value. Very popular question for us, especially electrical people. Very important question. And of course, many people give the correct answer. Clear, guys? So this is the total discussion regarding half wave and full wave. But don't worry, in this full wave, mathematical discussion is there. We'll be taking after the break. Clear? Take the break and come back. Take the break for 15 to 20 minutes of time and come back. We'll complete this full wave rectifier type instrument and we'll solve the questions. Clear? Take the break and come back for 15 to 20 minutes. So generally for voltage measurement, right? Mukul Jagtap, generally for voltage measurement, right? Right. Take the break and come back. Let's come back. Right. Now in this Fourier rectifier type instrument, right? Let's have the mathematics. What is the formula? I average is equal to V average by R total. V average by R total. Right now, sir, what is V average? 0.9 times of VRMS by R total. Sir, in this entire circuit, what is R total? RS plus in each and every path, 2 diodes will be there. So therefore, we need to consider 2 times of RD. Therefore, here RS plus 2RD plus RN. This is I average. Clear? Right now, after that same discussion, what we require? We require RS value. So therefore, we can say RS value to get which value? IFSD. RS value to get IFSD. Okay, right, sir. What is RS value to get IFSD means? In this I average place, we have to keep IFSD because that I average value is shown by the PMMC. That should be the maximum. The value should not exceed its maximum value. So therefore, IFSD. And what is V average? That is 0.9 times of VRMS by RS plus 2RD plus RM. Okay, now we can write RS plus 2RD plus RM is equal to 1 by IFSD into 0.9 times of VRMS. 0.9 times of VRMS. So what is 1 by FSD? Simply sensitivity. Sensitivity, right? Here we can write sensitivity, SDC, 0.9 times of VRMS. Okay, therefore we can write RS is equal to SDC 0.9 times of VRMS minus 2RD minus R. This is what the RS is equal to SDC 0.9 times of VRMS minus 2RD RM. This is one form. One more formula we can write for SDC into 0.9. I'm writing as SAC. So sensitivity DC into 0.9. I'm writing as sensitivity AC. Right. Is it for getting maximum value of IFSD? Yes, that is what correct, Shiva? Correct. Here, SAC minus 2RD minus RM. Right? So this is which value? RS value. SAC times of VRMS minus 2RD minus RM. This is RS value. Again here, where SAC is equal to 0.9 times of SDC. 0.9 times of SDC. So how is it happening? Let us prove it. SAC is equal to 0.9 times of SDC. Okay. What is sensitivity? 1 by IFSD. 0.9, 1 by 1.11. SDC again 1 by IFSD. Okay, sir, AC means RMS, DC means average. So therefore, what we can write? Therefore, IRMS is equal to 1.11 into I average. That only we have got in full wave rectifier type instrument. Clear? So this is the total discussion regarding half wave and full wave rectifier type instrument in detail. Clear? Based on this, how the questions will be given 1 mark and 2 mark in the gate, as well as for other people, ESC questions also will be taken. No need to worry. But the point here is, in this note I gave you average responding RMS indicating okay. But second note is there, very important. Sir, rectified type PMMC instruments are calibrated for sinusoidal RMS value or any other waveforms of RMS value. Means always be clear, this is the practical scenario. Whatever the rectified type instrument is available with us, all the rectified type instruments are calibrated for sinusoidal RMS only, but not for non-sinusoidal RMS. You may be asking the question, sir, why not for non-sinusoidal? Means you know that very simply, sir, out of available all waveforms, which is the standard signal, which is the basic signal, which is very popular signal, means sinusoidal signal only. That's why all the rectified type instruments are calibrated for RMS values of sinusoidal supplies only in the practical scenario, right? Suppose people are asking the question, sir, if I want to design for square wave type, if I want to design for triangular type of RMS value, means you need to mention specially to the manufacturer. Then only they will design according to your requirement. If you are not saying anything, simply they will say, right, rectified type instrument means they will calibrate the average scale of PMMC instrument into RMS scale of RMS scale, that to sinusoidal waveform only, but not other waveform. Therefore, second note is, what is it? Rectifier type instruments are calibrated for RMS values of sinusoidal signals only, or sinusoidal signals. Right, sir, if these devices are calibrated for sinusoidal signals, what is the problem here? Be clear. Sir, whatever the device available with us, it is calibrated for RMS values of sine wave, either full wave or earlier topic half wave. But if I give, right, to this entire device, if I give, suppose if I give square wave, if I give triangular wave, now tell me, does it show, kindly concentrate, does it show RMS value of this square wave, RMS value of triangular wave? No. Why? These are calibrated in general for RMS values of sinusoidal waveforms only, but not square or triangular or something else. So that's why what will be there? If I give non-sinusoidal signals as the inputs, definitely error will be there. That error is called as waveform error. And how to determine that error? We are having some numerical question, no need to worry. So that's why, what is the point here? Rectified type instruments are calibrated for RMS values of sinusoidal signals only. Clear, right? Then waveform error. This error name is waveform error. Waveform error is present. Then waveform error is present when non-sinusoidal signals are applied. non-sinusoidal signals are applied. This is very, 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 very important. That's why the rectifier type instruments itself indicates calibrated for which one? RMS values of sine wave only. If you want to design it for separate other waveforms, you need to mention clearly to the manufacturer. Otherwise, they will simply calibrate for sinusoidal only. These two are the conclusions in the entire rectifier type instrument. Any more confusions? Kindly let me know. Any confusions? Kindly let me know. Clear, guys? Right. So on this topic, in this chapter, we can say, right, what are the corresponding questions available in the GATE pattern as well as other competitive examinations pattern. Now let us take the questions. First, I'll start with the conceptual, very simple question. Then we'll move to the 2 marks model in the GATE paper. Right. Let me take the questions. Simple question. Imtiaz Pasha, is it required to save separately half-wave rectifier or full-wave rectifier? By default, which is manufacturers? I did not understand your question. Can you elaborate, Imtiaz Pasha? So they can answer your question. Right. What is the answer for this? Right. Very, very simple. Here, what is the question? Response to. Response to the PMMC, the rectifier type PMMC, rectifier type moving coil instrument. Response to always average. Peak value, RMS wrong. Average value of all the waveforms. Yes, it is responding for average value, but indicating RMS value related to the sinusoidal waveforms only. Very good, very good. All of you have given the correct answer. Clear? Right. Now let me take one more question. A full wave rectifier AC voltmeter reads the true RMS value of the input waveform. A full wave rectifier type AC, totally AC voltmeter, reads the true RMS value of the input waveform. Is it true or false? First assertion statement is correct or wrong? Respond, guys. We're missing something. Many people are giving correct, but we're missing small thing. Here's given that true RMS. Is it possible to read true RMS of the corresponding? No, definitely error will be there. No, but your doubt is genuine, right? Your answer, see, sir, we have calibrated for RMS value. Yes, you have calibrated, okay. But my question is, whatever the input we are giving, is it obtained exactly by this device? No, because it has its own error. It has its own error. It is also having its own error, definitely. And due to this, connections also, some errors will be there. Therefore, automatically error will be there. It is not possible to read the true value anytime. It is not possible to read true value anytime. So that is the reason why the answer here is true RMS value of the input waveform means assertion statement is wrong. Assertion statement is false. Right? No doubt, average value is being converted into RMS. But can we say, yes, after conversion of RMS, the 2.35 is there. True value is exactly 2.35. No, measured value true value, definitely difference will be there due to internal connection, due to internal meter resistance, etc., etc. Error will be. That's why true is not possible. Suppose if it is given like this, simply voltmeter reads a RMS value. Okay, no problem. But he has given that true RMS. Obviously, statement is wrong. Yeah, that's what I told you. Yes, yes. That's why if true is not given, then it is okay. Then it is okay, correct. But if true is not given, that will not be the question, right? Generally, you will give correct only. That's why to confuse you, to give you the negative mark. Yes, this is the model. And the second reason, the full wave rectifier type AC voltmeter has a rectifier unit first, which feeds its output to the PMMC indicative instrument. Is correct. First rectifier, output of the rectifier is given to PMMC. So therefore, reason statement is true. Reason statement is true. Correct. Clear, guys? Right? Let me take one more question. As many as possible questions I will take. An AC voltmeter uses the circuit shown below. Yes, this is the circuit. This one, full wave bridge rectifier, where the PMMC meter has an internal resistance of 100 ohm. So therefore, what is the meter resistance? Rem is equal to 100 ohm. Requires a DC current of 1 milliampere full scale deflection. Therefore, IFSD nothing but I average nothing but 1 milliampere. Assuming the diodes to be ideal, the value of RS to obtain full scale deflection with 100 volt RMS. So therefore, V input, that is V RMS, is 100 volt. What is asking? Find out the value of RS. Kindly try this. Whatever the formula I gave you already, try this. Right. Vinita, one doubt asking. VI is fed, no sir. Then how output of rectifier can fed this? So kindly concentrate in this. The full wave rectifier type AC voltmeter has a rectifier unit first, which feeds its output. Which outputs? Rectifier output to the PMMC. You are missing. I'm going to the first topic here in this. Kindly concentrate. In this rectifier type instrument, first rectifier output is fed to the PMMC indicating rectifier first, its output is fed to the PMMC. Is it clear? Is it clear, Vinita? Input is not fed. Output of the rectifier is fed to the PM. That is what our topic. Right? Okay, now try this. Yeah, very good, very good, very good. Bhavana, Nayan Sanjay Kalaskar. Yes, Abhijit. Yes, give the correct answer. Make it, make it. Mahesh, can you check it? You've given 89, but answer is there 89. Right, very simple. I average is equal to V average by RS plus 2RD plus RM. What is V average? 0.9 times of VRMS by RS. We don't know. Diode resistance he has not commented, so 0 plus RM is how much? 100 ohm. Okay, now, sir, what is I average? 1 milli, 0.9 into VRMS is 100 by RS plus simply RS is equal to dash. Vamshi Maya, kindly check it. Almas Ali, kindly not, it is not the B option. Sunil Wagmer, 8.9 milli ohm. What is it milli? How do you get milli? You will be getting 89.9 kilo ohm. Simple calculation. This is 900. It is coming over here 900. So 90 into 1000, 90,000. 90,000 minus 100. So 89,900. Simply 89.9 kilo. So answer is option C. Clear? Right. The same model. Let me take one more question. Try this. Anyone? Come on. Right. Right. And one student is asking that Shiva Prasad, Simha Shiva Prasad, sir, if he is not mentioning IFSD, then what will be the RS value? You are missing the topic again. What is our entire condition here? We have taken the entire discussion of our what is our necessity. The instrument must be protected such that the current should not exceed the full scale value. That is our topic. If the full scale value is not given, that is not at all the practical requirement. The practical requirement is IFSD so and so. The current should not exceed that value. Therefore, how much RS is to be kept over there. That's why definitely in the question they will mention IFSD. Even though they are not given this IFSD notation like that, it should be treated as IFSD. Then only we can find out the current. We can find out the resistance. Otherwise, we cannot find out the resistance for any value just like that. So that's why for full scale value of deflection, corresponding resistance. Clear, Shiva Prasad? Right. Very good. Many people give the answer. Yes. But here, simple point I'm giving here. Same thing. Earlier question, this one, both are same. But here, 100 kilovolt. Okay. 100 kilovolt. 50 hit supply. Right. Fed to a rectifier ammeter using a bridge rectifier. Okay. Using a bridge rectifier. Okay. Yes, this is a bridge rectifier, for example. Nothing but bridge rectifier means, of course, full wave rectifier. Right? Now, its output is given to PMMC. Its output is given to PMMC. Clear? Right. Through a capacitor, what do you mean by through a capacitor? Instead of using the resistance, he is connecting one capacitance. Nothing but CS. So far you have taken RS. Now we have to take CS. That's it. And the instrument full scale current is here. Ammeter of the rectifier instrument reads nothing but simply I is equal to 45 into 10 power minus 3 ampere means it should be treated as full scale deflection. Then only we can find out the CS value. That's what the point. That's why whether it is mentioned or not mentioned, our element calculation is towards the maximum flow of current. That's why we need to treat IFSD only. So what is the CS value? Very simple. Sir, I average is equal to V average by R total. We should not write. We should write Z total. Nothing but opposition we can write. Total opposition. Normal language I'm writing. Right, sir. In this entire data, he has not commented regarding diode resistance and he has not commented regarding meter resistance also. That's why we can write simply 0.9 times of VRMS by R minus JXC. We can write anyway R is 0. So therefore, only magnitude I'm taking the magnitude as just XC. Just X. So everything is there. Sir, what is average? 45 into 10 power minus 3. 0.9 times of VRMS is 100 kilo by XC. After getting this XC value in terms of ohms, everyone knows that XC equal to 1 by 2 pi FC. XC is equal to 1 by 2 pi FC. So therefore, C is equal to 1 by 2 into pi into 50 into XC. What is XC value? That's what. Come on, tell me the value. Shreya Shashi, can you check it? Vishnu Ajit, sir, PMMC is calibrated to read RMS value. Calibrated to read RMS value. It is not showing that it is showing value, etc. No, simply the average value flowing to the device is being given. That's what the procedure. Again, still people are giving different options A, C, D, etc. And you are going to get 15.9 is first option. 15.9 into 10 power minus 10 farad will be there. After giving this much of calculation, kindly use the calculator and find out this. See, Dinesh Rampur, right? Instrument reads 45 ampere means it is RMS. No, not that. That is not the meaning here. The instrument current is always to be taken as average value in the calculation of RS. In the calculation of RS, right? So therefore, kindly go back and what we are taken here: RS value calculation, IFSD, I average. This only we have taken as the total. So that's why average value only. Which why that current has to be treated as full scale value? Can't it be average value and calculate? See, that's what I'm saying. That's why follow my each and every step. I average is to be IFSD. I average is something is flowing, but that current should be the maximum possible current to have the safe operation. Means I average, IFSD, both are same only. That only have taken here also. That only have taken here also. You can write IFSD also. No problem. Right? If you want me to write here, I can write IFSD, no doubt at all. Already I gave you this. That's why I'm requesting everyone to follow each and every step. After my explanation, if any doubt is there, yes, you can. But while I'm writing, while I'm explaining, don't type any question. Right. Akshay, sir, ammeter, voltmeter calculation, no difference. See, calibration, no difference. Calibration, no difference. Because only the scale value is multiplied by 1.11 or 2.22. So no problem. But this is current, that is voltage. In that way, difference will be there. But calibration, no difference. No problem. Clear? No, Akshay, no, nothing. Same calibration. Clear, guys? Right. Let me take one more question. Right. Take 2 minutes of time and try this. Take 2 minutes of time and try this. After that, based on this in-depth models, I'm going to take. Anyone answer? Option B, C, different options are there. Okay, right. Let me calculate this. See, what is the question? Kindly read this carefully. Here, the scale of a full wave rectified type average sensing meter is calibrated to read RMS for ideal sine wave signal. So what is it? RMS value of sinusoidal waveform only. It is being calibrated. Form factor 1.11 clearly has mentioned. Okay, right. Determine the multiplying factor of the meter if it is used to measure RMS values of square wave. RMS values of square wave means a square wave is given. I want to measure RMS value of square wave, but that square wave is given to rectifier type instrument in which the scale calibration is done for sinusoidal waveform. Then what is a multiplying factor we require? That's what he is asking. Most of the cases, people are getting confused between these two because 1.11 or 1 by 1.11 confusion. Let me take now clearly step by step elaborated I am writing. After having the good practice, within 1 or 2 steps, you can write it. First of all, square wave, right? Square wave is given. To which device square wave is given? Rectifier type instrument. So that kindly concentrate here. This is the, what is it? Waveform representation. Right here. So what is the waveform representation? Square wave is given to the PMMC, sorry, to the rectifier instrument. Okay. If it is given to rectifier, what will be the output of the rectifier? Here, half wave is, what is it? Conducted, and other half wave is also conducted. Clear? Sir, what is its average value? Its average value is, what is the average value? Vm. Okay. What is its RMS value? Vm only. I hope everyone knows this. RMS value of square wave is equal to average value of square wave is equal to its maximum value. Yes, average value is maximum. RMS value is also maximum. Clear? Now tell me, this is given to which one? PMMC. Given to PMMC. But this PMMC is already being calibrated to read. What is it? RMS value of sine wave. So therefore, this PMMC, what is it? Calibrated for RMS of sine. Calibrated for RMS of sine. Therefore, what we can say now? Therefore, measured value, or I can say shown value is how much? This is the average value, and it is calibrated for RMS of sinusoidal means the form factor multiplication will be there. No, therefore here 1.11 times of Vm. This is the measured value. Are you clear up to this, everyone? Right? Okay. Now, sir, what is the true value? What is the true value? Very, very simple. Sir, what is the RMS value of square wave? Square wave, right? RMS value. Vrms is equal to V maximum. RMS value is directly true value, Vm. But measured value, how much? Vm into 1.11. Now he is asking, what is the multiplying factor? What do you mean by that? Here, measured value. 1.11 times of Vm into correction factor we can say, or multiplying factor also we can say. But he mentioned clearly in the question like multiplying factor. So therefore I'm keeping multiplying factor should be equal to which value? VM. Sir, why? That all I'm writing here. This is, what is that? V shown. Okay. And this is V true. So therefore, what should be the multiplication factor? Therefore, multiplication factor is equal to 1 by 1.11. So therefore, answer is, what is it? Second option. Clear, guys? Right. See, Sangeeta and Yashwant and Shubham Kurmet. Here, don't type while I'm explaining. Sir, explain again. Explain again means you are not listening and you're typing that explain again. So you'll be missing the topic definitely. You'll miss the topic definitely. After completion of my question, at any cost, I will explain. But while I'm explaining only, if you're typing, 100% you will miss the topic. So that's why I'm requesting everyone, don't type while I'm explaining. After completion of the topic, I will ask that is it clear or not? Say yes or no. Again, I will explain, no need to worry. So unnecessarily, don't miss the topic. Unnecessarily, don't miss the topic. Right? Now, I'm explaining again. Kindly concentrate. Right. See, very simple. Yeah. Square wave is given. What is the square wave true RMS value? Everyone, what is the square wave true RMS value? I have written here. Square wave true RMS value is maximum value. This is general basic point in network theory, analog, etc. Everywhere you get RMS value of square wave is equal to maximum. Okay. But what is the measured value? Means square wave is given to rectifier. Rectifier output is this. Rectifier output is given to PMMC. PMMC reads which value? Average value. Response for average value indicates RMS value. Okay. Average value is what? VM. Means whatever the PMMC we are using, that response for VM, concentrate here. Small topic but confusing. Response for VM, but it is already being calibrated for RMS value of sinusoidal signal. Therefore, measured value, what is that? VM, it is responding. VM, it is responding, right? Responding for VM, but showing which value? RMS value of sine wave. Therefore, average value into 1.11. What is average value? VM, maximum value. VM into 1.11 is the shown value. So that's why shown value is 1.11. If any confusion is there, this is Vmax. This is also Vmax. Vmax. Clear? Actually, what is its RMS value? Vmax. How much is shown? 1.11 times of Vmaximum. Then what will be the multiplying factor? What do you mean by that? Multiplying factor, if anytime he is asking, the measured value and the true value should be equal. Means in order to make those equal, how much factor we need to multiply? Therefore, V shown into multiplying factor equal to V true. What is V true? V maximum. What is V shown? 1.11 into V maximum. So automatically, what is it? V max cancel, multiplying factor equal to 1 by 1.11. This is one thing. But newcomers may be getting one doubt. Like, sir, why are you taking like this? V shown into multiplying factor is equal to V true. Why not like this? V true into multiplying factor is equal to V shown. Why only taken like this? Why not taken like this? Means very simple logic. For other people, I told in the electrical measurements, but new people, kindly concentrate. What is the meaning of this? Here, shown value is corrected and equated to true value. Is it correct? Here, true value is corrected. True value is corrected. True value is adjusted to make it equal to shown value, which is correct practically. Tell me, which is correct practically? Measured value is to be corrected and equated to true value. Measured value is to be corrected equated to true value is correct. That's why, yes, measured value, nothing but shown value. Corrected means some factor he's asking that should be equated to true value. That only I have taken. Right. Ruturaj Jalamkar. Sir, what is the answer for a triangular wave is given? Take that as a homework and give me the answer. Right? Take that as a homework and give me the answer. And Urukonda Satish, sir, measured value is 0.9 times of VM. Kindly check it. How 0.9 times of VM? Kindly go back and check it. Right? Simply, what is it? 1.11 V maximum. 1.11 V maximum. So therefore, multiplying factor is 1 by 1.11. Yes, this is 1 by 1.1. No doubt, as it is a new model, definitely confusion. That's why I have taken again. I have taken the complete revision. Clear, guys? And here, people are asking, sir, if instead of square wave, triangle is there. Suppose if I extend for triangle, some other people will ask like, sir, what is a rectangle? Some other people will ask like some other waveform. So that's why understand one waveform. After that, you take any waveform, answer will be with you. No need to. That's why I'm requesting everyone. While I'm speaking, you should not type anything. While I'm speaking, you should not type anything because the moment I started here, you may be getting the doubt. Immediately if you're typing, you'll be missing. Again, the entire total topic will be doubt only. That's why if any doubt is there, don't worry. That may be clarified. That may be clarified in this topic. That may be clarified in the next page, etc. Maybe. That's why kindly wait until I conclude. Clear? Right. And Sai Charan Reddy, all I told you, don't ask the repeated models kindly, especially for square wave measuring. All I told you, if you want to go for especially for square wave, calibration for square wave, you need to order. You need to order the manufacturer like, I need to have the calibration for square wave. I told you already, that is generally, but it's a rare cases. Universally, sinusoidal waveforms will be there. That's why waveform error will be there. That's what the point. Clear? True value means given value, nothing but unknown value. True value means given value, nothing but unknown value, whatever we need to measure. Clear? So this is the entire thing related to the correction value. Right? Okay. Now, let me take one more question. If this is clear, all coming questions will be very much clear. Now, kindly concentrate. This also I will do entire solution. I will do entire solution. No one should try. I'm saying already, no one should try because after this explanation, 1 or 2 questions I'm going to give as the practice questions. I'm going to give as the practice questions. So kindly concentrate. No one should write. Right? A full wave rectifier, a full wave bridge rectifier, AC voltmeter, automatically bridge rectifier, AC means rectifier type instrument, has its scale calibrated to read RMS of sine wave, automatically RMS of sine wave in general. If something special case is there, they will mention. We'll solve that question also. The amount of error in reading expressed as percentage of true RMS value. He is asking error value. Now tell me, sir, calibrated for sine wave, given which value? Sawtooth. One student asked just now, I told you about square wave. I have taken the question regarding square wave. Sir, other than the square wave, something else is there? Yes, I will be doing. No need to worry. That's why wait. Definitely all models will be covered. Right? Kindly no one should try anything. Kindly concentrate. Right? This is 2 marks model in the earlier paper. What is that? Here. First of all, what is this waveform? Sawtooth waveform, right? Okay, sawtooth waveform. Okay, right. Everyone should be aware of the corresponding basic points regarding sawtooth, square wave, etc., etc. All the things must be definitely you have to. You should be aware of all these points definitely. What is that? Sawtooth waveform RMS value is dash. What is it? VRMS value of sawtooth is V maximum by root 3. V maximum by root 3. Okay. Sir, what is V maximum? In the given question, he has given that 150. So therefore, 150 by root 150 by root 3. So therefore, now tell me, this is the true value or measured value? This is the actual value or measured value? This is the actual value or measured value? Akshay Guruvarapan. I am coming to that only. How the error is present, I am showing. Everyone, is it the actual value or measured value with the device? This actual value. So therefore, this is called as actual value, or we can say true value. Actual value or true value. Okay, right. But do we get this value exactly? No. Why? This is given to bridge rectifier type of instrument in which sinusoidal calibration is there. Then what will be the measured value? If the measured value is there, true value is there, we can find out the error corresponding. Now I'm taking here. What is that? Sawtooth is given to. Kindly concentrate. Actually, these many steps are not required, but for your clarity purpose, I'm taking all these many steps clearly so that you can erase your doubts. Okay? Kindly concentrate. Sir, this is VI. What is that? Sawtooth. Okay? This is a sawtooth. Given to which one? Rectifier. Given to rectifier. Sir, sawtooth given in the question is there is no waveform on the negative side. So no problem. Therefore, what will be the output of the rectifier? Output of the rectifier is also same like this only. Okay. Now tell me, concentrate here. This is the rectifier output. This is the rectifier input. Okay. So rectifier output given to PMMC. Yes or no? Right? This PMMC reads which value? Reads nothing but shown value, etc. Otherwise, I'm writing response to. First, I'm writing response to. Which value? PMMC always responds to average. So response to average value. Okay. Therefore, what is the V average value of this sawtooth waveform? Anyone? Average value of sawtooth waveform is dash. Average value of sawtooth waveform is dash. Everyone? Vm by 2. V maximum by 2. Very good. V maximum by 2. What is that? 150 by 2. 150 volts by 2. That is 75 volts. Okay. 150 by 2. That is 75 volts. Okay. Sir, this PMMC calibrate for which one? RMS values of what is it? Sine wave. So therefore, response to average, okay. But what is that? Indicates which value? RMS value. What is the RMS value formula? Average value into form factor. Average value into form factor. Which form factor? 1.11. Why 1.11? He has mentioned full. So full means 1.1. Now tell me, this is the true value. This is the which one? Shown value, indicated value. Therefore, we can say that which value it is? Measured value. Measured value means shown value. Measured value means shown value. Clear? Right. Now tell me, what is the error formula? Those who are newly attending these measurements, can you take this formula? We'll be studying this formula, entire details about this formula in the electrical measurements. What is that? Measured value minus true value by true value into 100. Okay. What is measured value? 75 into 1.1. 75 into 1.1 minus true value is how much? The true value is 150 by root 3. Therefore, 150 by root 3 by 150 by root 3 into 100. Into 100. So therefore, find out this value, you will be getting the error value. Okay, one second. Don't give the answer. Sir, this is the error. One student has already typed one question. Sir, how do you get the error, etc.? Who is that person? 1 second. Akshay. Right? Sir, we are multiplying with correct multiplying factor for the corresponding waveform to get the correct value. Then how the waveform error will present? See, whatever the factor you are adding to make the error is 0. Error is already there. That's why you're finding the factor. In the earlier question, we have calculated the factor. In this question, we are finding the error. That's it. Otherwise, in this question also, if I'm asking about finding the factor, means what is that? Measured value into multiplying factor is equal to true value. What is measured value? 75 into 1.11. So multiplying factor is equal to true value is 150 by root 3. You are equating these two, means automatically error was there. You are minimizing, you are making that error equal to 0. Therefore, multiplying factor something will be there. If you are adding, if you are keeping the multiplying factor in the formula, means you are making measured value and true value both are equal, means error was there. You want to eliminate that error. That's all the point. That's why first question multiplying factor, second question error calculation. Everyone, give me the error value. I hope it is clear. Akshay. Right. Sunil Wagner, kindly, before giving the answer, kindly think of it once. Kindly think of it. Don't mind, kindly think of it. Yes, many people gave the correct answer. Sunil Wagner, 99.03. 99.03. 99.03 means that much error is present here? No. And Dinesh Rampur, at multiplying factor equal to 1, no error. Come on here. How can you say that? Multiplying factor equal to 1 means this and this both should be equal, but both are not equal. Yes or no? So therefore, here error will be minus 3.86%. After giving each and every step, give me the correct answer kindly. Yes. Yes. Minus 3.87. Or 86, no problem. So answer is minus 3.8. Clear? Yashwant, Kuchi Yashwant, kindly concentrate. If he is asking find out the error, find out the error. If he is asking to find out the multiplying factor, find out that. That's what the point actually. In this question, if you want to find out the multiplying, you can find it out. No problem. What's the multiplying factor? 150 by root 3. 75 into 1.11. So and so is the multiplying factor. Clear? Right. If in order to clarify this further for newcomers, kindly concentrate. See, simple logic means simply practical scenario I'm giving. Yeah, Dinesh Rampur, we are trying to reach multiplying factor equal to 1. That is correct. But you are given 8 multiply for 1. No. So I thought that multiply factor is directly equal to 1. No, not exactly. Right, correct. Right. Right. Kindly consider simple logic. Yeah. Those who are having doubts still different terminology, no, the simple logic can give me. See, kindly concentrate. I have 90 rupees. I have 90 rupees, but I want to get 100 rupees. This is the true value. Kindly observe clearly. This is the true value means actual value. A means some value. T means true value. This is measured value. Tell me, difference is there or not? Everyone, difference is there. So I want to find out the error means. What is it? 90 minus 100 by 100 into 100. What's the value? Minus 10%. This is error. Suppose if I want to find out, multiplying factor, sir, I have 90, but I want to get 100. So how much factor must be included? This is multiplying factor, or you can say correction factor, or you can say some other simply factor to be included, no problem. So what is that? Multiplying factor is 100 by 90. 100 by 90. Therefore, what is it? 1.11 for example. For example, 10 by 9, 9 ones are 9 ones are 9 ones are, for example, 1.1. Now tell me, 90 is less than 100. So therefore, how much factor is to be included means more than one, yes, multiply. But now tell me, people are saying that, sir, multiplying factor is included. If it is included, error will not be there. You are missing one small thing. If you are including the multiplying factor itself indicates error was there. That's why you are including the multiplying factor. That's what the point. If he is asking error, do this. If he is asking multiplying factor, do this. At least now it is clear, I hope. Right? Mukesh, multiply factor, correction factor, both are same, no problem. Sahil Singh, yes, correct, both are. And Logan Narayanan, kindly concentrate. 150 is not my value. 150 is given. 150 maximum value has given in the question. V maximum 150. Kindly see the question. 150 is given in the question. It is not my assumed value. It is mentioned in the question. Right. Like this, any doubt you clarify, I will explain directly or with one example. Clear? Right. Let me take one more question. At least now I'm expecting answer from everyone. Right. At least now give this. Right. Kalyan, why we are taking root 3? Where? Here, kindly, this is the basic point. RMS value of sawtooth waveform itself formula is Vm by root 3. That is a basic point. Basic terminology, network error, n-log terms are basic electrical engineering itself is RMS value of sawtooth is Vm by root 3. That is the basic point. Clear? Right. Now, tell me this answer. Option D, option B, option C. Okay, you people are covering all options. Okay, nice. Very simple again, same discussion. Now I'm giving the simplest way procedure. A voltage waveform shown in the given figure is applied to an ideal full wave rectifier voltmeter. Kindly concentrate. How can we save the time in the objective paper? How can we directly? So far I have taken each and every step. It is given to rectifier input, output is given to PM, like that I have taken. Now direct answer. Square wave, right? Concept, square wave. What is the RMS value? Vrms is equal to V maximum is equal to, he has given maximum as 100 volt. This is a true value. True value. Clear? Right. So what is the measured value or shown value? Measured value or shown value. So what is the measured value means? PMMC response for average indicates RMS. So what is the average value? 100. So what is square wave? RMS value, average value, maximum value, all are same. And the two calibrated for RMS of sine wave, RMS of sine wave, full wave. So therefore automatically measured value is, what is that? We measure is equal to, we measured is equal, what is it? 1.11 times of V average. Therefore, 1.11 times of 100. So therefore, what is the value? 111. 111 volt. Right now, kindly concentrate. What he is asking? The voltmeter will read. The voltmeter will read means will show which value? We measured 1.11 times of average value of this 111. So directly answer is 111. Clear? Suppose in this only I'm adding the question. Find out the error. Simply percentage error is equal to, what is that? Measured value is 111 into true value is 100 by true value is 100 into 100. What is the value? What is it? 11%. At least now clear. He has not asked the error, but I'm giving error calculation also to clarity, to have the clarity. Clear? Right. At least now, I hope you got the clarity. Take one more question. Take this as homework question. Take this as homework question. Ramakrishna Rapilli. Sir, square wave average here is 0, no sir. So kindly go to the basics. I'm requesting everyone. Kindly go to the basics. Srishti Rawat. So tell the answer for homework questions. And answer is A. Okay, I'm giving answer also for verification purpose. Directly multiply 1 by multiplying factor, that is 1.11. Which one you are asking, Sai Charan Reddy? Here, take this question as a homework question. Let me take one more question. Very simple question. Already we have done the same model, but values are different. Make it fast. Mukul Jagtap, why am I giving answer means after having your solution, you should know that is correct or wrong, etc. So that's why kindly I'm giving answer for that purpose only. If you're getting something as the answer, you can understand that okay, this is wrong. I need to try again for that purpose. Yeah, Sai Chanity we can do directly like that, but for that you need to have good practice. Once you have the good practice, you can multiply directly, no problem. Come on. Yes, very good. 8.5 kilo ohm. 8.5 kilo ohm. So direct answer. Very good. 8,500, but 8.5 kilo. What is the answer here? I average is equal to V average by R total. What is V average? It is a full wave, no? 0.9 times of VRMS by RS plus 2RD plus RM. Okay. What is I average? He has given 1 milli. 1 into 10 power minus 3. 0.9 times of VRMS is 10 volt by RS plus 2RD. Diode resistance is not given and meter resistance is given as 500. Therefore, RS is equal to, this is 9,000 minus 500. So 8,500. But few students have given that 8509.009. How did you get that? Simha Shivaprasad, 8509.009. Here we are not going to compensate the diode drops in our subject. So diode related topics you are going to study in the other thing. Those diode errors will be always present. Right? Simply germanium instead of germanium silicon, like that we replace it, but we cannot compensate completely. Diode loss will be there definitely. That very small we can neglect it. Clear? Let me take one more question. The input impedance of permanent magnet moving coil PMMC voltmeter is infinite, but ideal meter. Assuming that the diode shown in figure below is ideal, the reading of the voltmeter in volt is. The reading of the voltmeter in volts is. Tell me. Anyone? Right. 4.46. Many people give that 4.46. Others? Come on. Make it fast. Make it fast. Yes, yes, that's what I'm waiting actually. Few people are giving Amrit Sagar given as 0 and Pratyush Punyapu given 0. Right? Many people are giving 0 as the answer because small confusion, that too. That 0 is there in the options. That's you need to take more care. Right. Kindly concentrate. So what is the procedure here? Concentrate. Sir, in this, during the positive of cycle, what will be there here? First point, during positive half cycle, diode gets, what is it? Forward bias. Diode gets forward bias. Therefore, no reading in the meter. Therefore, no reading in the meter. Sir, why? Concentrate. Sir, for positive half cycle, the entire signal flow through this only. Why? This is forward bias. Forward bias means it acts as short circuit. So therefore, no signal through this resistor, no drop across this. Therefore, no reading of the meter. Okay, right. Second thing, during negative half cycle, during negative half cycle, the diode gets reverse biased. The diode gets reverse biased. Therefore, reading of the meter is not 0. If you understand this, automatically we can eliminate the fourth option. Because many people are saying that yes, the answer is 0 like that, but actually not 0, because in the negative half cycle it will be acting as open circuit. Therefore, total signal will be passing through this. Automatically drop will be there across this. Clear? Diode is ideal, so therefore forward bias 0 resistance, reverse bias infinite resistance. This 100 kilo ohm is this resistance. Clear? Right? So answer is not 0. Okay. Sir, what is the given value? Vi of t equal to 14.14. What is the value? Sine, which value is given? 314t. Sine 314t. Therefore, what is the V maximum value? 14.14. 14.14 volts. Okay. Now, what is its average value? V average is equal to, it is acting as half rectifier only, means half cycle only conducting. So V average is equal to Vm by pi. What is it? 14.14 by pi. What's the value? 4.5 ohms. 4.5 ohms. After that, simply I average is equal to V average by R total. V average by R total. V average already we have got it. 4.5 by, what is R total? This is 1 kilo ohm and this is 100 kilo ohm. 1 kilo and 100 kilo. Diode is anyway one cycle, 0 resistance, one cycle infinite. No need to take. So therefore, what is the value? 1 kilo ohm plus 100 kilo ohm. Any confusion in this? I average is 4.5 by, what is it? 101. 4.5 by 101 kilo ohm. Sir, what is the value of current? 4.5 by 100k, for example. So milli will be there. So answer will be 4.46 into 10 power minus 5 amperes will be there. Clear? Right? Now tell me, what is the current flowing through this resistor? The current flowing through this resistor is how much here? Simply 4.46 into 10 power minus 5 amperes. But what he is asking, voltmeter reading. So voltmeter reading is current through this resistor into resistance of this value, this resistor. So simply what we can write, therefore voltmeter reading is equal to what's the value? Current flowing through, that is I average, and resistance value. I average is 4.46 into 10 power minus 5 into resistance is, what is it? 100 kilo ohm. 100 kilo ohm. 100 kilo. What is it? 10 power 5, 10 power minus 5 cancel. So 4.46 ohms. Clear, guys? Right. Ashok Gajapati Raju, kindly concentrate. 100 kilo ohm is for diode value or resistance value. Kindly see the question. Diodes are ideal. So therefore, this resistance is this one. In between they have given, but diodes are ideal, means the resistance 100K is resistance value. The examination, that will be the diagram. So we need to understand by the corresponding data given. Clear? Right? Any confusion? Kindly let me know. See, yes. Okay. Shiva, as altimeter reads RMS value, but you took it as average value. Kindly concentrate. Try to understand the terminology. If he is asking meter reading in terms of RMS value, that is different. But what he is asking, the reading of the altimeter in volt means the current flowing is I average into resistance only. After that, it will indicate which one, that is different. So 4.46. Answer is there. Yes, your doubt is genuine, but based on the option, you need to go. But in the options, both will not be there. No need to. Clear? Yes. Input impedance of PMMC is infinite means. Input impedance of PMMC infinite means the meter resistance is need not to be taken. Meter resistance is simply neglected under the conduction mode. Under the conduction mode, input resistance means PMMC. What is it? Infinite resistance is there. Infinite resistance is there means current received or current drawn will be zero. Therefore, the error due to internal resistance of the PMMC meter is neglected. Yes, that's why meter resistance no need to take. That's what the point. Yes, no loading defect. Very good, very good. Clear? Let me take one more question, last question, then we'll go for next chapter. Right. Same model what I have done. This is also homework question. A rectifier type instrument uses a bridge rectifier and has its scale calibrated in terms of RMS values of sine wave. It indicates a voltage of 2.22 volt when measuring a voltage of triangular wave shape. Estimate the peak and RMS values of the applied voltage. Also calculate the error. Right, this part is same, but before calculating this, we are going to find out the peak value, that is maximum value, RMS value, etc. Those values also he is asking. As some people are saying that don't give the answer, I'm not giving this. Yes, you will. You need to solve it and you need to come with the answers in the tomorrow's class. In this earlier question, current limiting resistor function is not given, so no need to worry. Pratyush, right? Current limiting resistor means we can treat this as the current limiting resistor. If you want to treat, you can treat this as a current limiting resistor, but he has not mentioned. No need to worry. Yes, this is there. No need to worry. What are the questions I'm taking? Yes, take all these things. So this is the entire discussion regarding analog voltmeter, that is rectifier type instrument. Rectifier type instruments. Clear? Next chapter is digital voltmeters. Digital voltmeters. So what is the digital voltmeter? First of all, before going to the digital voltmeters internal total discussion, entire discussion, what are the advantages of digital instruments? What are the advantages of digital instruments over analog? Let us list out all those. Advantages of digital instruments over analog instruments. Right now, what are the advantages? Very simple. Here, high sensitivity. High sensitivity. Sir, why high sensitivity means? These are with respect to digital signals. Digital signals automatically compared to analog signals, the digital signals are having which one? Discrete step fashion, means clock pulses will be there. As the clock pulses are there, the response will be faster and the response will be for smaller values also. Therefore, high sensitivity will be there and high accuracy. High accuracy, high sensitivity, and good resolution. We can say better resolution. Better resolution. And what is the speed of response? High speed of response. And so what is the other advantage? These are general advantages: high sensitivity, high accuracy, better resolution, high speed, etc. But frictional losses will be there or will not be there. Frictional error will be zero. Why? In this digital meter, the pointers moving over here and there, inertia, etc. will not be there. Therefore, what is it? No frictional error. No frictional error. Right? No frictional error since, right, no moving objects or no moving parts, we can say. Just like PMMC or MI, etc. Pointer is moving, spindle is rotating, etc. Bearings and all will be there. Due to that, frictional error will be common. But in this digital, there is no frictional error. And here we can say no observational errors also. No observational errors. Why? Observational error means kind of concentrate. Those who are new to this, simply analog instrument is this is the pointer, for example. Pointer is like this. If I observe exactly from opposite side like this, if I observe, I can observe the value perfectly. But if I observe from this side or if I observe from other side, definitely due to the shadow of the pointer, I may be or that other person may be standing from this side and viewing from this side, definitely observe the wrong reading. That is called as observational error, or simplest terminology is parallax error. Therefore, in this number system is there. Like this also, if you are observing number system is there, no, automatically the observational error will be very, very less. Actually, very less we can say, almost 0. That's why no observational errors. And here, very important advantage is, right, that is auto ranging facility. Auto ranging is available. What do you mean by auto ranging? Kindly concentrate in the electrical instruments, that is PMMC, MI, etc. When I was taking all those, I told one point clear. What is that? Once the instrument is designed for 0 to 5, for example, once this is designed, always its full scale value is 5 only. Always its full scale value is 5 only. Are you clear? Once it is designed, always its full scale value is just 5. Okay, that's why full scale value is constant. Nothing but its range. Range means full scale value. Range is constant. This instrument range is constant. But in the digital instruments, the range will be changing automatically. We can change the range. That's what is called as auto ranging facility. Auto ranging facility is available. Very important. And one more general point we can write: can be connected to the computer, can be programmized also, so that we can write, yes, programming facility. Nothing but these are connected to the computer. We can dump the program, according to the program also we can run. But analog instruments, no program operation, no what is it, facility to connect to the computer and all. So that's why ultimately digital instruments are having what is it, more number of advantages. But so what about the cost? What about the cost? Generally, compared to analog instruments, the digital instruments are little bit more cost. But nowadays, as the entire world is getting digitalized, the cost is getting down, the cost is getting reduced. Therefore, cost is also no problem at all. So all these are the advantages available in the digital instruments over analog instruments. Clear? So this is the introduction regarding digital instruments. Yes, no human error, etc. All errors will be less, we can say simply. Clear? Right. Now, in this digital altimeter, according to the syllabus given in GATE as well as ESC, we are having, right, digital altimeters. Which type of digital altimeters available? Right, those are 3-digit DVM, means digital altimeter. 3-digit DVM. Second one is 3.5-digit DVM. 3-digit DVM, 3.5-digit DVM. Third one is 4-digit DVM and 4.5-digit DVM. Like this, 4 types of devices are there. Right? If you understand these two clearly, 3.5, 4.5, 5.5, 6, any device you can design. So that is basic discussion is 3-digit DVM. Right? After that, 3.5-digit DVM. But what is half a digit? Everything will be taken, no need to worry. Right? Deepa Javeja, right? I have not explained anything regarding this. Only I told you in the analog instruments, the range is constant. The full scale value is constant. But in this, full scale value can be varied. How? I'll explain in this entire discussion. No need to worry. What is it? I did not explain anything. But I told you in the analog instruments, range is constant. Full scale value is constant. But in this digital altimeter, full scale value is not constant. That I have taken. Clear? Okay, right. 3, 3.5, 4, 4.5, 5, 5.5, etc. Right? Generally, see, in the syllabus, it is given like simply digital altimeter only. DVM, just I told you, kindly listen carefully. digital voltmeter, DVM, digital voltmeter, right? So generally in the digital notation, generally we are having the syllabus like voltmeter topic only. That's why I'm taking digital voltmeter directly. Clear? Right. Now, before starting the 3-digit digital voltmeter, let us discuss about the digital voltmeter first. What is digital voltmeter? How the corresponding block diagram, how the structure is there, etc. So let us take digital voltmeter. Otherwise, directly I'm taking the figure digital voltmeter. So how the block diagram and all, kindly concentrate. I'll be showing the figure. One second. Kindly wait. I'll be taking that figure. Kindly wait. Right. Kindly concentrate. This is the right. This is the figure. See, digital voltmeter. In this, generally, what is the type of signal we have practically? That you have to concentrate. Generally, analog signal will be there. Generally, analog signal. Whatever the signal we are observing or we are using practically, all those signals are analog signals. Generally, sir, this analog signal is to be given. This entire box is generally taken as digital voltmeter structure. So internally, whatever the analog signal we are giving, that will be given to the entire device, and that will be connected to structure called as attenuator. Nothing but along with that range selector, two blocks will be there: attenuator and range selector. So what is attenuator? Attenuator means it is attenuating the signal. What is that meaning? Means simply in our electrical terminology, we can say voltage divider circuit. Suppose three resistors are like this, for example. Here I have given some voltage V1. If I take voltage across this, do we get V1? No. V1 is the applied voltage across three resistors, but I am taking voltage across two resistors only. Therefore, automatically we can say attenuator, and correspondingly reducing the signal means in the electrical terminology voltage divided network. After that, sir, where we have to keep the switch, that will be selected by range selector. So based on the selection what we are taking, the voltage will be available. This is VM, V measured, sorry, V to be measured, V unknown, V to be measured, or we can say VI also, we can say V true values, we can say. Here I'm writing as V in. Why V in means after the range selection, whatever the value is there, that is given to the dual slope ADC. Otherwise, if you're getting confused, you can erase this one. You can erase this simply. You can give the terminology V true value. And here, output of the range select, like that, you can give it, no problem. Simply, I'm giving some terminology. Okay, right. After this will be given to very important block, that is ADC. Whatever the signal we are having, that is analog, but Mriganka Fukan. What do you mean by that? Mriganka Fukan. What do you mean by that? Come on. Respond kindly. Your pen size is big, writing in the board is bad. So you're talking about this one, all these things. Can you tell me? No. Let him or let her clarify this. Right. Okay, you're talking about this one, right? Right here. Simply, this is a figure what was there. I'm showing as it is diagram. Kindly concentrate. This is some input signal given to the entire device attenuator. Signal is what is it? The range selector switch. Based on that signal will be selected. Corresponding output will be available here. Okay. After that, kindly concentrate. Sir, this will be given to ADC, dual slope integrating type. Dual slope integrating type. Dual slope integrated, that is ADC. Sir, why means analog signal is to be converted into digital, because our device is digital instrument. So therefore ADC. But in your entire practical case, in other subject also, so many types of analog to digital converters are there. But out of all those, the best analog to digital converter is dual slope integrating type ADC. And in our entire digital voltmeter chapter, dual slope integrating type ADC only will be used. This is also one question for our electrical people. The type of ADC used in digital voltmeter, like 3-digit, 3.5, 4 or 4.5, etc., is dash. That is dual slope integrating type ADC. That's what the point. Okay. After that, digital converter means the output will be in terms of clock pulses. Okay. Based on that, digital drivers will be there. Those digital drivers, nothing but digital counters will be there, right? In the digital drivers, counters will be there. those counters will be counting these clock pulses. Okay, based on that count, corresponding 7-segment code will be displayed. Correspondingly, display will be available on the corresponding digital readout. This is the overall explanation, overall just block diagram explanation. Clear? Clear? Mangesh Kalman, yes, okay, thank you. Clear, guys? Right. So this is the total introduction regarding the entire digital. So therefore, what are the stages? Analog signal given to the attenuator based on the range selector switch. Range will be selected. How I'll tell you. Based on the selection range, the signal will be there, converted into digital. Based on the corresponding clock pulse will be produced. Those clock pulses will be counted by the counters, and that output will be automatically 7-segment code. That 7-segment code will be displayed in the corresponding digital readout. Suppose in this digital readout, suppose 3 digits are there like this. This is called as a 3-digit DVM. Suppose 4 digits are there, 4-digit DVM. 3.5 is there, 3.5-digit DVM. Like that will be there. So based on the designing only, we can say so and so device is 3-digit, 3.5, 4 or 4.5, etc. This is the simple block diagram expression. But no need to worry, sir. What is happening? Everything will be shown clearly one by one with the corresponding elaborated structure in that 3-digit, 3.5, etc., etc. But this is just overall explanation. Right. People are asking, what is the purpose of ADC? Kavyasri. ADC means whatever the analog signal is there, that should be converted to digital. Why? Our device is digital altimeter, means the digital signals based only the process should be there. Therefore, it is analog to digital converter is compulsory. Suppose analog to digital converter is not there. Analog signal is directly coming. Do we have number display? No. We'll be having the pointer movement, that is PMMC, MI, EMMC, etc. That is electrical analog devices. But our topic is digital, means analog devices must be converted into digital. Okay, next. Shiva, could you explain the function of range switch again? Range switch means the name itself indicates range selection. That's it. Elaborate explanation will be done later, but only overview I gave you. Block diagram means overview. Analog signal, attenuator, based on our requirement range selection, based on that signal will be there, that will be converted to digital, that is clock pulses. Clock pulses, the generated clock pulses will be counted by the digital drivers, and corresponding display will be there. That's what the overall discussion. No need to worry. Don't think like, sir, this is being completed. Nothing is, no, only block diagram explanation. After that, I'm taking the 3-digit DVM, clear cut explanation, step by step explanation I'm taking. Clear? Right. Now I'm starting 3-digit DVM. Very important for us also, electrical students also. Very important. Clear? Right. Now I'm starting the topic now. Three-digit DVM. DVM means digital altimeter. Okay, kindly concentrate. I'm not showing the block diagram directly. I'm going to build up I'm going to build up one block, so that I'm going to combine all the blocks. So finally, the total device will be available. First one. So what is the signal available here? Signal available is analog. Analog signal, definitely. You can name it as VI, VM, anything, no problem. Simply analog signal. Okay, sir, this will be connected to attenuator, nothing but resistances. Here, 3 resistances. Okay, some number R1, R2, R3. Okay, right. And this is called as input attenuator. So simply I'm giving the name input attenuator. Okay, right. So after that, here switch. Right, these are the switch positions. These positions are A, B, C. These switch positions. Okay, and here selection switch will be there. Nothing but you can keep it A, you can keep it at A or at B or at C also. Okay, after that. This is range selector switch. Clear? Only I'm showing the block diagram. What is that? Analog signal given to attenuator. After that, based on our selection, the signal will be attenuated. Yes, signal ABC. Sir, why do we keep it A? Why do we keep it B? Or why do we keep it C? Or what will happen if we keep it A or B or C? Everything will be taken in detail. That is what our main explanation. Clear? Right. Here. See, all I told you, for every 2 hours, I'll give the break. Kindly, while I'm explaining, if you ask, sir, break, sir, break, sir, it will be demotivating to the faculty, such that we are not clear, etc. For every 2 hours of time, I will give the break. This is my way. So no need to worry. Until I give the break, kindly don't say break, break, break. Automatically, the corresponding person who is explaining will get demotivated. Right? You need the break. Even we also need the break. So no need to worry. Right now, sir, this range selector switch, after that what will be there? Dual slope ADC, nothing but simply ADC will be there. Yes, I'm taking ADC. Right here, dual slope integrating, dual slope integrating type ADC. Okay, right. Sir, what will be its output? Its output will be, right, clock pulses. Sir, how many clock pulses will be generated? How many clock pulses will be generated? That depends on your selection. Who will be operating this one? Operator only, I'll tell you that. Okay, some number of clock pulses. So these clock pulses will be given to, these clock pulses will be given to the counters. These clock pulses will be given to the counters. So what is that? Simply decade counter. One decade counter here, one more decade counter here, and one more decade counter here. So why only 3? Everything will take. Right? Now, this will count. So decade counter means up to which number it will count? Simply 10 numbers. 0, 1, 2, 3, 4, etc. Up to 9. Up to 9. Okay? So therefore here. After that, it will give the carry pulses. So it will be starting its count when ultimate. It also will be counting up to its maximum count, and it will be giving the carry pulse. So it will be driven. Clear? So why only 3 decade counters? Why only 3 resistors? Everything will be explained. Don't worry, Pratyusha. I will explain. No need to worry. Why 3? Why 3? Everything I'll tell you. Okay. So my question is, sir, decade counters will count the values. Okay. But what will be the output? How the output of the counter? Digital electronics completed, I think. Now tell me, what is the output of the decade counters? In which form? The output of the decade counters or any counters will be in which form? Can you respond? The output of the counters will be in which form? Can you tell me? Electrical engineers, kindly tell me. Binary form, digital form. One student has given 1, and Sangeeta giving the discontinuous form. 8-bit binary. Dinesh, pulse. Vishal, LK 01. Very good. Ashish Raj gave the correct answer. BCD form. Binary coded decimal form. Don't say just binary. This is in BCD form. Why? The counters will be counting from 0 to 9 only. After 9, if it is a 10 number, simply 0 means 000. 1 means 0001. 9 means 1001. But 10 means, do you get this type of count? No, this is just binary. But counters will be giving in terms of binary coded decimal. Therefore, 10 means what will be the value? 10 means 0 will be given as 000 and 1 will be given as 001. Means second digit is started. Therefore, second step is to be started. This is called as BCD form. This is called as BCD form. Are you clear? Yes, Gurudatta Behera, correct. BCD form. Clear, guys? So therefore, BCD form. So therefore, what is BCD form is 4 lines. Yes. Like this, 0000001, like that. Yes, corresponding output is available. This is called as BCD code. BCD code. After that, what will happen? Finally, what we require? We require 7-segment code. We require 7-segment code. What is 7-segment code? How the 7-segment code is available? Everything will be discussed after the break. Right? After that, what will be there, etc. After that, each and every step I will explain, and with corresponding step by step, switch A, separate explanation, switch B, separate, switch C, like that. Total explanation will be taken. Clear? Take the break and come back. Class is up to 8:30. 2 to 8:30 is a session. I hope everyone knows that. Yes, take one more break here and come back. We'll continue the class. Yes, Vishnu Ajit mod 10 counter, decade counter means 10 number, no problem. Mod 10 counter or mod n counter. I want to know 10. So mod 10, no problem. I'll give those names later, no problem. Okay, take the break and come back. We'll continue. Yes, come back. Right. Let us continue. Here, the decade counters are always giving the output count in 00012 to 10011. That is the nature of the binary counter, or any counter we can say. Few people are asking that, sir, why only BCD code? Come on here, come on. Go to digital transition, have the basics. The counters will be giving the count in terms of BCD form. Sir, this is the BCD code, but what we require? 7-segment code we require. So that's why that BCD code is being converted into BCD code is being converted into, right, 7-segment code by 7447 IC. 7447 IC with some device, with some integrated circuit IC. The BCD code is being converted into which one? 7-segment code. So therefore, we are going to have the corresponding display on the digital readout. We can say 3-digit display. Okay. Now here, this is the corresponding code. Which code? 7-segment code. So 7-segment code will be into picture here. Right. So this is 7SC. 7-segment code. Right. So that 7-segment code is giving the display in the corresponding display structure like this is the 7-segment code. This is the 7-segment code. This is the total block diagram of, right, 3-digit DVM. Now I'm giving the total discussion. Sir, why only so and so number, etc. means our device is 3-digit, right? 3-digit DVM means only 1, 2, 3 digits. Yes, sir. In order to have 3 digits, what we require? 3 7-segment code paths. Thereby 37447 ICs, 3 BCD code paths, 3 decade counters only. Then only we can call this as 3-digit DVM. As this is a 3-digit DVM, here also switch positions must be 3 and resistance also must be 3. Then this device is called as 3-digit DVM. Many people already typed the doubt, sir, why only R1, R2, R3, why not R4? Means our device is which one? 3-digit DVM. So therefore, everything must be 333 only. First point. Clear? Right, sir. In this internally, one more switch arrangement will be there. Like this, 3 switch arrangements will be there. This is A, B, and C. Here, switch. This is connected to +5 volts, and this is anyway return path. Sir, this switch position is connected to this switch position is connected to one LED will be there. That is decimal point LED, and one more switch is connected to one more LED will be there, light emitting diode, because our 7-segment code is 7 segments. 1, 2, 3, 4, 5, 6, 7. So 7 LEDs will be there. 7 light emitting diodes will be there. Okay. After that, here like this 3. Now the people are asking that, sir, why can't we have 4 switches internally? Kindly concentrate. Why can't we have 4 switches internally so that decimal point over here D, like this people are asking. First of all, decimal point at this position is allowed or not allowed technically? Tell me, decimal point is allowed or not allowed at this point? Means I'm asking about this D. So here I am going to be manufactured. I am going to give, what is it? LED here. So therefore, this will be with respect to one more corresponding switch position. Thereby, the switch is kept at D. Supply will be given. Yes, decimal point will be glowing. But is it acceptable or not technically? Tell me, everyone. Is it acceptable or not? Kindly concentrate. It is not acceptable technically. It is not acceptable technically. Sir, why? Means if any number is there, simply if I write point, does it have any meaning? No. After this decimal point, some digits should be there, either 1 or 2 or 3, etc. etc. But after writing some 8, for example, 8 point, does it have any meaning? No. If you are keeping the decimal point, definitely after the decimal point, one digit must be represented at any cost. Right? After the decimal point, one digit must be represented at any cost. So therefore, if you are keeping the decimal point, definitely digit must be. That is a mathematical rule. This is not my digital or measurement rule. Mathematical rule itself, we cannot say 8 point. If we say 8 point, immediately we're expecting that 8 point. Come on, tell me, we say. What do you mean by that? 8.1 or 8.8 or 8.99, like some number. Therefore, if you're keeping the decimal point, definitely one digit must be there. But here, only 3 digits are there. Only 3 digits are there. Yes or no? Therefore, what's the value here? 3 digits are there. There is no question of decimal point over here at all. Clear? So that's why the simple shortcut technique I'm giving here, 3-digit DVM. Kindly concentrate. 3-digit DVM, 3-digit places, 3 decimal places, 3 7 segment code paths, 3 7447 ICs, 3 BCD code paths, 3 counters path Martin or decade counters, and 3 ABC switches, and 3 R1, R2, R3 attenuated resistance. These are the simple idea. It is not shortcut. Concept based, I'm giving simple shortcut way to remember. Clear? Okay. Jayesh Gupta, sir, but this would increase the range to a higher value. Which one? Which one increase the range to a higher value? Jayesh Gupta, kindly elaborate your statement. Decimal at last. See, no. If I keep decimal at last, no one should say the range is extended. Why? If the decimal at this point is there, decimal has no meaning until we have the digit after the decimal. That only I have given here. If I keep the decimal point, definitely after the decimal, number should be there. If number is not there, mathematically there is no meaning. Otherwise, at least 0 should be there. 0 is there means one digit is there. Of course, 0 has no value at this point, no problem. But that place is having the value. That's why. What is it? It is called as 2-digit display. But can I say that 8 point only 1-digit display? No. Why? If I'm keeping the decimal point, after the decimal, definitely corresponding number, corresponding digit place is to be there. So that's why here there is no question of decimal point. And the two, sir, if I keep the decimal point, range will be extended. No, we cannot keep, we should not keep the decimal point at all at that position. I hope I'm clear now. Clear? Right? Clear, guys? Right. Bhavana, I have not given the operation. Kindly wait for 5 to 10 minutes. Operation will be given. Then your doubt will be clarified. That is what actual total discussion. Now, simple logic. Sir, this device is with us. This device is with us. Okay. This display is visible. And kindly concentrate. Whatever the range selector switch is there, this is by operator. This will be operated by the operator. Means, suppose we are the operator. Yes, we are having the device. Switch will be there. Yes, we can rotate the switch according to our requirement. But what is our requirement? Right now, we don't know. Simply, I want to keep it A. I want to keep the switch at A. Sir, why do you want to keep the switch at A? I'll tell you. Sir, if I keep the switch at A, kindly concentrate. If I keep the switch at A, automatically, this switch will be connected at A. Which one? This switch will be connected at A. Are you clear? If I keep the switch at A, automatically this switch will be kept at A, will be moved to A. That is called as internal connection will be there. That is called as two switch. Two switches are internally connected, but we cannot operate this directly because this is a switch internally available. We can operate only this switch. That's why I'm clearly mentioning by operator. So that's why all the switches are not on at the same position. If we keep the switch at A, right, then this will be there and decimal point, this switch position will be coming over here. Then automatically this decimal point will be glowing. Then what is the display? Decimal point 000 is the display. What is it? If the switch is kept at A, decimal point 000 is the normal display. Clear? Second thing, sir, if I keep the switch at B, kind of don't ask the question like why are you keeping it B? I'll tell you that. If I keep the switch at B, this switch will be moved to B position, then this decimal point will be glowing. Automatically, the supply will be disconnected from A. This will not be glowing. So what is the display now? 0.00 at B. What is the starting display? 0.00. Clear? Okay, sir. Here, if I keep the switch at C, if I keep the switch at C, this will be moved to switch C. Therefore, the decimal point will be coming over here. Therefore, this will be glowing 0.0. Therefore, C position 0.0. Now tell me, where is the question of this dot or this decimal point glowing? No way. So that's why there should not be and there will not be any decimal after this digit. So this is a simple idea. Now tell me, all the switches are on at same position? No way, no way. Malavika, kindly wait. Right. Okay, Shirisha. Okay, up to 8:30 means up to 8, 8:05, up to 8 or 8:05 I'll be taking the class. After that, I'll be having the doubt session. Right, up to 8:30, the doubt session will be there. Okay, right. Clear? So this is the total discussion. If we keep this switch position at A, it will be moving to A. If I keep the switch at B, it will be moving to B like that. Simply based on this movement will be available. That is what the internal link. Clear? Right. Now tell me, first one, I'm taking the operation for almost 30 to 35 minutes. No one should type anything. I'm requesting. If you are typing something, so it is not clear, that is not clear, total topic will not be clear. I'm openly saying. So that's why every point will be clarified step by step, step by step. If you're having any doubt at the first point, no need to worry. That will be clarified in the coming discussions. No need. That total 30 to 35 minutes of topic is there. Kindly be clear. Don't write anything. Just look at the screen just like that. Okay, don't write. Sir, first of all, so in this entire device, what is the starting display? 000. Okay, that is called as rollover digits. We can say 000. Okay, so I'm taking here 000. I'm not keeping the switch position 000. Sir, one count is being started. Suppose one clock pulse is given. One clock pulse. How means you have selected the switch position? One clock pulse is given. Sir, this will be counted by this. If it is counted means 0001. So this will be converted into 1. So therefore 001 will be the display. Clear? So therefore the second means the coming step will be 001. Now suppose two counts are happened. 0 0 like that, it will be keep on going up to 999 count. Okay, sir, after 999, suppose, kindly concentrate, after 999, suppose means number display is 999. Decimal point I'll tell you later. Sir, suppose it is 1000 clock pulses or more than 1000 is coming, for example, then what happened? For example, 999 is there. Suppose one more clock pulse is generated by the switch position, etc. What will happen here? Already 9 is there, right? 9 plus 1 count, 10. But do we have any chance of display of 10 in one digit place? No. Therefore, what happens here? This will be going to 0 and giving the carry pulse to this. Therefore, already 9 is there. 9 plus 1, 10 again. What is that? 0 will be here. Again, 1 will be here. Means again carry pulse. 9 plus 1, 10. 0 will be here. Nothing is there too. Allow the carry pulse. So therefore, this will be reset position. So therefore, what is the final position now? 0, 0, 0. Therefore, 9 plus 1, 10. So 9 plus 1, 10. 9 plus 1, 10. Other point is nothing, because if I write like this, it becomes 4-digit device. But our device is only 3-digit device. That's why it will not be this. This is called as simply reset position. Means going back to initial position. Now tell me, from here to here you can count, or here to here you can count. How many number of counts or how many number of steps are there in this 3-digit DVM? How many number of counts or how many number of steps are there? Means 1000. So therefore, how many? 1000 counts or 1000 steps. This I am writing as 1 into 10 power 3 counts. Now tell me, in the 3-digit DVM, how many number of counts are available? 1000 counts or 1000 steps. This is simple mathematics. This is simple mathematics. Clear, right? Simply 0 to 999, 0, 0, 0 to 999, whatever 1000 counts. Clear? This is called as rollover digits of corresponding 3-digit DVM. Clear? Fine. Now, I'm keeping the switch at A. Kindly concentrate. Operation is being started. So kindly concentrate. Right? I'm keeping the switch at A. I'm keeping the switch at A position. Fine. Okay, one more doubt. One student is asking, sir, why only 5 volts? Come on here. You need to have some small basics in the digital instrument. Generally, 5 volt supply, 12 volt supply will be there. That will be with respect to some battery notation. Internally, battery will be there with respect to some supply. Simply in the digital instrument, in the analog also, VCC plus 5 volt you are taking. That is standard supply voltage internally available with respect to some battery notation. Okay, right. Now, kindly don't get deviated. Don't type anything. All I told you, if anyone is typing while I'm explaining, I will remember those names. I don't clarify their doubts. Okay, so that's why kindly, until I complete the entire thing, keep on listening. One by one, 3 switch positions are there. 100% I'm giving the guarantee it will be clarified without typing if you concentrate on my explanation. So kindly concentrate. It doesn't mean that I don't clarify, but don't do that. Okay, right. See, first one, switch is at A position. Why are we keeping? I'll tell you. Simply, I'm taking the operation. If we keep the switch at A position, sir, we are keeping this, but automatically this will be moved to here. Then automatically, which display will be there? Starting display. So therefore, concentrate. What is the starting number? Decimal point 0, 0, 0 is the starting. Suppose if you have given the input and we have chosen the corresponding switch A position and the clock pulsar only one, for example, some input, we don't know that input, right? Only one clock pulse is there. So only one clock pulse is there means this counter will count. It will give 0, 0, 0, 1. This will be giving us one display. But this counter has not started its count. This counter is also not started its count. Therefore, 0, 0 as it is, 1 will be there. So therefore, decimal point 0, 0, 1. Suppose next count like that I'm giving first step, okay, and here 0, 0, 2. Like that, it is keep on going up to decimal point 999. After that, if suppose one more count is coming, after that one more count is coming, for example, right, then it will become decimal point 0, 0, 0. Clear, guys? Right. Now, again, how many counts are there? 1000 counts are nothing but 1 into 10 power 3 counts. 1 into 10 power 3 counts. Clear? Okay. Now the concept is being started. Sir, in this entire thing, how many counts are there? Full scale counts are how many? 1000. So first point I'm writing. Full scale counts 1000, that is nothing but 1 into 10 power 3. So why 1 into 10 power 3? I'll tell you later. Right? That's what the notation. Clear? Right. Second, sir, what is the minimum value measurable in this? In this entire thing, what is the minimum value? Of course, this is voltmeter. No, yes, voltage only every time. Now tell me, in this entire switchgear operation, what is the minimum value measurable? Don't answer. I will tell you. The minimum value measurable is, what is it? 0.000 means operation is not yet started. After the operation started, what is it? 0.001 volt. Sir, between these two, are we able to observe any value? No. So that's why the minimum value measurable, the minimum value observable is 0.001 volt. It can be written as 1 millivolt. So don't answer anything, just I will question, I will answer. Sir, in this switchgear position, less than 1 millivolt is observable or not normally. In this switchgear position, less than 1 millivolt is observable or not means not possible. Why? First, operation is not started means 0.000. Operation is started means first count itself is 0.001 only. 0.0005 not possible. Why? 4 digits or 5 digits are required. But our topic is only 3-digit device. That's why simply only 3-digit means below less than this is not possible. So minimum value measurable is this. Okay, next. Sir, what is the resolution? What is a resolution? I told you everyone in the electrical measurements and other people just take it for granted. This is a definition, direct definition. What is it? Resolution is the smallest measurable input change. Don't worry, I will give this point again. No need to worry. No need to worry. I will again give this entire details. No problem. What is it? Resolution is smallest measurable input change. Sir, what is the smallest measurable input change in this entire switch equation? 0.001 volt only. Therefore, what we can say? 0.001 volt. So therefore, 1 millivolt. Resolution in the switch A position by the structural operation we obtained is 1 millivolt. Vaishnavi Suryavanshi Sudarshan Suryavanshi. Kindly, all I told you, while I'm explaining, if you say that please explain, not clear, etc., means you are not at all listening. Take it for granted. All I told you, no one should type anything like please explain, please repeat, etc. Even you are not saying that I will repeat. But while you are typing 100% and give the guarantee, you will miss the topic. If any one statement is missed, continuation will be missed. Again, you're typing one more miss. Again, you're typing one more. Final topic will not be clear. All I told you clearly. Right? No need to worry. See, this is the online class. Network issues are very common. No need to worry. I will repeat again and again until you clear. No need to worry. Immediately, the network issue is there. Sir, explain again. So by typing that at least half a minute time, you will be missing some steps. So automatically, continuation will be missed. That's why whatever the network issue are there, etc., leave it. You listen first. In the switch A over, switch B is there, no repetition will be there. Switch C, one more repetition, so no need to worry. Okay, right. Next, sir, resolution is there. Sir, what is the one step value? Sir, each step value is 0.001 volt. What is that? 1 milli. Therefore, what we can write? 1 millivolt per step, or we can say 1 millivolt per count. Yes? One step 0.001, 1 milli. Second step 0.002. So up to 2 steps, 2 milli, 3 steps, 3 milli, 4 steps, 4 milli. Why? Our decimal point is coming at this position. Automatically we can say, yes, this is giving milli notation. Okay, right. Now, in this switch A position, last step, but be clear. Sir, how many number of counts are there? Full scale counts are 1000. Okay. Sir, 1000 counts are there. Into what is the count value? 1 millivolt per count. 1 millivolt per count. So count cancel, volt will be remaining. Yes. So therefore, 1000 into 1 milli, 1 volt. This is called as range. This is called as range. So therefore, what we can say from now onwards, 1 volt switch position gives which range of operation. Kindly concentrate. 1 volt switch A position gives which range of operation, means 1 volt range by the concept I have proved. But simple shortcut is, in the switch A position, as a decimal point is glowing here, first decimal point, left side, first decimal point, up to 0.999 volt only. So 0.999 means 1 volt only. Therefore, maximum value is equivalent to 1 volt. Therefore, range is 1 volt, we can say. Therefore, 1 volt range. Therefore, 1 volt range. Now, I'm going back. Kindly concentrate. I'm indicating one thing over here. Simply here. This position is called as 1 volt range position. Why? I'm not writing before explanation, I'm writing after my explanation. Sir, if the starting decimal point is glowing, that is giving which one here? 1 volt range position. 1 volt range position means more than 1 volt is possible? No. Why? Already give the operation. 0.999 itself is the maximum. So no question of more than 1. That's why 1 volt range operation. Clear? Right. Now, kindly concentrate. Switch B also same type of explanation, but revision. I'm not leaving like switch B same, switch same. No, I will explain that so that it will be clear. Then 3.5 instrument, 3.5 digit DVM will be very much clear. Okay, right. Next, B. Switch B position. Switch is kept at B. Kindly concentrate. Sir, we are moving which switch? Range selector switch, which can be operated by operator. Okay, I'm moving this to B position. If I'm moving this to B position, automatically this switch will be coming to this B position. This switch will be coming to B position. Sir, if this switch is coming to B position, automatically this decimal point will be glowing. But here small doubt, people. Sir, this and this both will be glowing. People are saying, but is it possible to have the glowing of two? No. Why? This switch is connected here only, disconnected from A. Automatically, the second switch position will be there. Therefore, in the switch B position, what is the starting display? 0.00. Starting display is 0.00. Right after that, so first count is generated after giving some input. A switch B, some clock pulses generated. I'll tell you how many number of clock pulses, etc. with example. Therefore, 0.01. Okay, this is called as which one? First step. Okay. Like this, keep on going. 0.02 volt. Keep on going. Maximum number will be 9.99 volt. 9.99 volt. After that, suppose if you are giving one more clock pulse, automatically 0.00 volt. Sir, even we are going for switch B position, how many counts are there? How many counts are there? 1000 counts only? Yes. 1000 counts. So therefore, 1 into 10 power 3 counts. 1 into 10 power 3 counts. Clear? Right. Now the doubts will be clear. Sir, what is the full scale count value? Full scale count or full scale counts. How many? 1000 only. 1 into 10 power 3 only. 1000, 1 into 10 power 3. Those are full scale counts. Okay, sir. Here, same discussion. What is the minimum value in this? Sir, minimum value is 0.01 volt. Below this and above 0, not possible. So therefore, minimum value is 0.01 volt. This is equal to how much? 10 millivolt. Okay, after that. Sir, resolution is dash. Resolution is smallest measurable input change. Yes, minimum value is this only. Less than that, nothing is possible with this step. So with this switch position, we can say, therefore, 0.01 volt, or we can say 10 millivolt. We can say 10 millivolt. Clear? Right, after that. What is the step value? Each and every step or count value is one step. 0.01 volt means 0.01 means 10 millivolt. Therefore, 10 millivolt per count, or we can say 10 millivolt per step. Okay, now final step. Right? How many counts are there? 1000 counts are there. What is the count value? 10 millivolt per count. Okay, is equal to count cancel, 1000 milli cancel. What's the value? 10 ohm. So what is the range of operation here? 10 ohm. So 10 volt means it will read up to, it will show up to 10. Check it. Up to 10, 9.99. More than that, not possible. So 9.99 is nothing but 10. So range of operation is 10, but maximum value display is 9.99. Now tell me, device is same or different? Device is same, but based on the switch action which is provided over there, switch A 1 volt range, switch B 10 volt range, switch B 10 volt range. So that's why I'm giving here. This is which one? 10 volt range related decimal point. That is the point I gave you already. What is it? Auto ranging facility. Some people ask that, sir, what do you mean by auto ranging? Explain. Yes, auto ranging means device is same. By moving the switch A, switch from A to B or B to C or B to etc., range can be automatically changed. That is what called as auto ranging facility. Auto ranging facility. But this type of thing is not available in analog instruments. Therefore, these are possible in digital. That is very greatest advantage is this auto ranging facility. Clear? So that is what this can have. Clear? Right. Priyavat Raj. Sir, if switch is kept at B, then display will be 0.00. Come on here. Here, if the switch is kept at B, switch is kept at B, it will be here. This decimal point will be there means already 0 is there, 0 is there, 0 is there, 0.00. But you are saying that because you are not listened while I'm explaining, that you are getting this down. Suppose if you are saying that, sir, the display will be 0.00 only. No, why 0.00 means what is our device? 3 digit. But what is your answer? 2 digit. Our device is 3 digit. That is the reason why 3 digit places should be there. Yes, one more 0 should be there. If it is not there, this is called as 2 digit DVM. But our device is 3 digit DVM. That's why no one should, I'm giving no point. No one should remove the zeros by thinking that value is not there. No one should add the 0 by thinking that 0 has no value at all. No, right? Definitely, whatever the zeros are acceptable, keep them. Whatever the zeros are not acceptable, leave them. But don't keep unnecessarily, don't leave unnecessarily, because this is digit-based concept. This is not value-based, digit-based concept. Clear, Priyavat? Priyavat Raj. Priyavat Raj. Okay. Vinita, right? Resolution is same as minimum value. Yes, minimum value, nothing but smallest measurable input changes. Smallest measurable input changes. Yes, that is resolution. Right. Is switch automatically to be after input, not with range of a. No, yeah. This is by operator according to our requirement. What is that requirement I'm giving? I'm giving. What is it? Suppose I have the range 5 volt to 7 volt. I have the unknown. Come on, guys. I have the unknown input range 5 volt to 7 volt. 5 volt to 7 volt. Now tell me which switch position we have to take as an operator. Now you have to answer. Everyone should answer. My unknown input range is 5 volt to 7, but we don't know 5.5, 5.6, 6. We don't know. Only 5 volt to 7 volt range is given. In order to measure this, which switch position must be taken by you as an operator? Tell me, which switch position must be taken by you? Clear? Right. So many people give that B switch. Yes, yes. That is what the correct point. Vishnu Ajit, correct. That's why I told you this is the range selector switch is available outside to the operator for operation purpose according to the operator requirement. That's what the point. Clear? It will not be automatically moving here. I am giving the device. I am giving some unknown input. So according to the knowledge of this instrument, okay, my input range is 5 to 7 volt. So which position? B position. For example, as of now, suppose I'm giving 0.5 to 0.8 volt, 0.5 to 0.8 volt, then 0.5 to 0.8 volt. Which range we generally we talk about? Yes, switch pole. That's what the point. So that's why the selection of switch range must be by us operators. Right? I'm taking this entire expression. If it is automatically done, no problem. Give the input, it will change automatically. 2 minutes, stop it. But actually, we need to operate it. That's why this much of it. Right. Switched battery side is operated automatically. Whatever the switch position you're choosing here, that will be operated automatically. Clear? Right. I'm giving 2 minutes of time. Kindly everyone, write all the values related to switch C in your notebook or on the paper, etc. by taking 1 minute of rough work. After that, I will write and verify it. I'm giving 1 to 2 minutes of time. Switch C position, everyone has to write. And after my explanation, you need to verify. Take your own time kindly. First, 1 to 2 minutes of time. Come on. Come on. I hope it is done. Right. Okay. Let me write this. Switch is at C. Kindly concentrate. Switch is at C means this decimal point will be glowing. Okay, this decimal point will be glowing. So therefore, kindly don't write only decimal point 0. It will become one digit device. So that's why 0, 0 will be there and should be there. Okay. First step 0, 0.1. This is first step. Like that, it is keep on going 0, 0.2. Of course, it is also only, and it is going continuously up to 99.9 volt. Okay. Finally, 0, 0, 0. So this is simply reset. Right. Now, what is the number of count? What is the number of count? 1000. So 1000 counts. It can be written as 1 into 10 power 3 counts. 1 into 10 power 3 counts. Clear? Right. After that, here, first one, full scale counts 1000. Right? 1 into 10 power. That's why very important question is in 3-digit DVM the full scale counts are dash. In 3-digit DVM the full scale counts are dash. 1000. Whether you take A position, B position, C position, it will be 1000 only. After that, sir, what is the minimum value? Minimum value is this only. So therefore 0, 0.1 volt. What's the value? 100 millivolt. 100 millivolt. After that, resolution. Resolution R is equal to, what is it? 0, 0.1 volt, nothing but 100 millivolt. 100 millivolt. Okay. After that, what is the step value, count value? Therefore, here 100 millivolt per count or 100 millivolt per step. Clear? So finally, what is that? 1000 counts are there into 100 millivolt per count. 100 millivolt per count. Count will be cancelled. 1000 milli cancelled. So therefore, 100 volt. Of course, it is a range. But many of you have given the correct answer. Sir, 100 volts range operation. Yes. But Dinesh, you have given 1000 volt. Is it possible? 1000 volt? No. 99.9 only. 99.9 only. Therefore, it is 100 volt range. Now I'm going back to this. I'm mentioning this is 100 volt range. Clear? Now, very important conclusion. Kindly consider. After having this entire analysis of switch A, switch B, switch C, finally, by the manufacturer, switch A 1 volt. They will keep it. And switch B 10 volt. Switch C 100 volt. Now tell me, if this device is given, automatically our sense say that, okay, if I keep the switch at one position, 1 volt range is the switch position. So therefore, 1 volt value is the maximum. Switch B 10 volt, switch C 100 volt. So automatically, suppose your value is 55 to 75 volt is there. Which switch position must be taken? Which switch position must be taken? So our normal common sense, what we can say, 55 to 75 means okay. Yes, up to yes 100 volt. Very simple. This is what called as actual, what is that? Selection of device or selection of switch position according to our requirement. Clear? So this is what the point. Now, I'm giving some more clarity for other people's point of view. Concentrate. So, your unknown input range is 55 to 75 volt. Okay. I'm giving 3 devices. I'm giving three devices. One is 0 to 1 volt device, 0 to 10 volt device, 0 to 100 volt device. Which device you have to prefer? Blindly you can say yes, 0 to 100 volt device. Okay, this is an analog instrument related question. Okay, same thing. What is that? 55 volt to, right? 75 volt is there. Three switches I'm giving. Three switch position means 3-digit DVM. 0 to 1 volt switch position, 0 to 10 volt, 0 to 100 volt switch. Now tell me which switch position you prefer. Simply, yes, that is what the point. Clear? Come on, guys. Can you let me know, is it clear? Step by step explanation I gave you, is it clear or not? That's why I told you, wait until I complete. Definitely clarity will be there. Step by step, step by step. First only switch A, that is first time you are injecting. So small doubt. Switch B, switch C, finally it will be clear. Right. Vinita, for different resolution, should we change resistors? Have you changed the resistors anywhere? No. And if voltage is 55.55, then what will be displayed? Come on here. 55.55 means we need to go for 4-digit device. 4-digit device. Suppose if we choose or if we go for 3-digit device, what will happen? We'll be seeing that with questions. No need to worry. Ashish Raj, 55.45 means simply 55.55, 4-digit device. Take it for granted. Suppose if you use 3-digit device, simple logic, 55.5. 1.5 will not be there. That's what the display. Clear? Right. Definitely, resolution is getting changed with the switch position. Right? How to get different resolutions, sir? Vinita, all I told you, as you are changing the switch position, resolutions are changing automatically. The switch position means resolution will be changing by smallest measurable input changes. That only they are changing. Right. Right. No, Sai Charan Reddy, we should not consider this as 100 volt. No, because after the very good question, Sai Charan Reddy, here, he is asking that, sir, after 99.9, if it is showing that 0.0 means, can we consider this as 100 volt? No. Why means concentrate. Suppose in this, concentrate here, 99.9 is there. Suppose after this, two counts are coming. Suppose two counts are coming, right? 9 plus 2, 11. But what is it here? It will read up to this only, 0 only. 0 only. 0 only means after this, you may be giving 1 count or 2 counts or 10 counts or 100 counts. Any count, 99.9. After this, 0.0 only. That's why we cannot treat this as 100. It may be more than 100 also, but we cannot decide. That's why 99.9 is the maximum. After that, if it is showing as 0.0 means, based on the concept, what we can say, it is more than 99.9. That's it. But 100 or 101 or 103, 104, we cannot decide. Right. Right. Okay. Vikrant, sir, can we? Oh, one second. No, one second. Right. What if I didn't choose any switch? So I can measure up to 999. Is that available? No. 999 means that is possible in the next device, that is 4-digit device. That is 4-digit device. Clear? Right. Imtiaz Pasha, correct? Right. For 2 volts, of course, automatically switch B position. Kindly don't ask anything regarding 4-digit. I'll be taking that. 4-digit I'll be taking. Right. Vinita Lagishit, 0.5 resolution. How can we get, sir? Where did we get 0.5? Where did we get 0.5? Sir, can we say that the switching range is like to 0 to 1 volt and 1 volt to 10 volt and then 10 volt to 100 volt? We should not say simply 0 to 1, 0 to 10, 0 to 100 only we say. But Okay, no problem. If you are dividing that, you can say that, no problem. Sweta Ahir. Sir, if you apply 4-digit value, like, how can you apply? That's what the point. You are asking that simply, sir, I have 0 to 1 ampere device, but I want to apply 100 amperes. What will happen? We cannot. But even though we apply like that, it will show 0, 0 only. Very good. Yes, 0, 0 only. Yes, correct. Shweta, correct. No. Sangeeta, after 0.00, can it be continued? It will not continue because it cannot have the capability to read more than the 1000 counts. That's why I told you 1000 counts is the maximum. 1000 counts is the maximum. After 1000 counts, don't think like the value will be continued. No, that will be the simply reset value. I told you already, reset value. Right. Negative value means negative display will be there. No need to worry. Before that, negative, one more value will be there. No need to worry. Nikhila. See, Singham Mamata, 3.5 digit not yet started here. 3.5 digit not yet started. Kindly try to understand. I'm explaining Telugu. 3-digit instrument matrame ayindi. 3.5 avaledu. I'm saying in English, 3-digit device is only done. 3.5 digit is not done. I'm giving in Hindi, 3-digit topic is 3-digit topic ही मैं लिया था. 3.5 digit topic will be taken later. बाद में आएगा, tension मत लीजिए. So that's why think about 3-digit DVM only I'm requesting. 3.5 बाद में आएगा और बहुत सारे topic भी है. Lengthy topic is there with 3.5 digit, no need to worry. Okay. Registers are given according to the corresponding device. It will not continue after reset. It will not continue. Right. Avinash Chimkar. Right. See, one student is asking that, sir, if I give the input signal like always it is increasing. Is it possible to measure? You are saying that in the network theory, this is a question here. 5 ohm. Kindly concentrate. This is main problem with my measurement. That is what? Understanding the practicality. 5 ohm is that no one should type anything. Kindly concentrate. Sir, if I give 10 volt, I am asking you to find out the current. What is your duty? 10 volt by 10 ohm, 1 ampere. Can you ask that, sir, if the voltage is continuously increasing, find out the current means, is it possible here? Definitely no. Are you getting point or not? That's why the value will be given for that particular value. This is the answer. Suppose if I give you 20, I is equal to 20 by 10, 2 ampere. That's what the question. That's why I'm requesting everyone. Before, you can ask any doubt, no problem. Before asking the question, try to analyze that question. You will get the answer 100%. But don't throw the questions on me directly because you will be losing the thinking capability. That's why, okay, I'm asking that, sir, if the input voltage is continuously increasing means there is no particular value. If there is no particular value, which value you will measure? Which value you will measure? Not possible. That's why particular value is to be given. That's not the point. Right. Alan Navin Sai, correct. Right. Sir, without connecting the point supply voltage, no. So that is a point here. What we were thinking is, sir, if this is not there, can we get a 999? Can we get 999? No, yeah. Simple logic. What you are missing, this simple mathematics you are missing. Normally, 999 is generally technically not acceptable. What you have to keep? 999. Something is not there means at least 10. At least 10. That is what the actual representation. Because if 999 is there, and I may be thinking that 0.1 may be there, 0.2 may be there, 0.3, which is there, we don't know. That's why, what is it? Insufficient data, we can say. That's why 999, right? 0.0. Then we can say, okay, exact 999. That is what the thing. But what we use mathematically, that is approximation based. But this is exact based. But I don't know who is asking this, but good question. Who is this? Satish, right? Satish. Who is this? Yeah. Urukonda Satish. Very good question. Sir, if I remove this, instrument operation is not being done. If you remove this, instrument operation is not being done. That is the reason why this will be there. 99.9 only. If you want to get a 999, the logic here is just a 999 technically significant figure based. We cannot accept it. Therefore, 999 point at least 0. Then it comes in 4 digit. That's a simple theory. Mathematically, practically you can write 999 something, but is it ended or is it continued? We don't know. So that's why 0. It will come in 4 digit device. Right. So for 9.5, switch B or switch C, 9.5. I'll tell you. But B is clear, no? B or C, which is better? I'll tell you. Right. So the battery switch operation is based on drain selector. Yes, correct. Sir, how do we give 5 volts to the, that is inbuilt? That is inbuilt with battery cell will be there. No, with that the voltage will be given. No need to. 5 volts is fixed. Generally 12 volts or 5 volts, but 5 volts is enough. No problem. No. 5 volts is for LED glowing purpose. That 5 volts is not with respect to our number display, etc. Only for glowing purpose. Some supply is required. LED should be activated for that purpose. Generally 5 volts. In the electronic circuit, generally 5 volts is popular value. That's why we use that. Okay, all doubts are done. Clarified. Right. What if we on switch C when 7 volt? I'll tell you that. I'll tell you. Right. So for switch A, my supplies, yeah, definitely. Simple logic here. If you are giving more than the range value, simply it will show 0. If you are giving more than the range value, simply it will show 0. Take it for granted. Now I'm coming to the laboratory. What is that? Yeah, all signals. No, because it is a 3-digit game. 3 registers. Yes. I already told you, Bhavana, correct. Yeah, right. Sahil Singh, correct. Yes, any signal. Right. Concentrate here. Sir, concentrate. I don't know whether you observed in your laboratory or not. In your laboratory, multimeter was there, etc. Like this. Suppose voltage range 2 volt, 20 volt, 200 volt, something is there. Okay, in the multimeter. Sir, on the display, 0, 0, 0, something 4 or 5 digits, some device I'm taking. Assume that some input is given. We don't know, some input range is given. Right? You have selected 2 volts range. Kindly concentrate. You have selected 2 volts range. Okay? If you have selected 2 volts range, I don't know, but many times it happened. Those who have done experiment strictly, sincerely, seriously in your BTech, they will come across this at least once in their BTech life. At least once in their BTech life. Or with your friend also, you will be experiencing this. Suppose if it is kept at 2 volt, assume that it may be 0, 0 point something, some display 0, 0, 0 will be there. You will think that sir, supply is given, it is showing 0. Immediately, unknowingly, without knowing anything, your friend or your lab assistant or your faculty might have told that, yeah, turn the switch. You have turned the switch. You have changed the switch to 20. Automatically, some number 9.99 or 12 point something, etc. is displayed. So what is the meaning? You have chosen the 2 volts switch position, but you are given greater than 2 volts indirectly or directly without knowing something. So therefore, more than the 2 volts you are giving, but you are choosing the 2 volts switch position, automatically more than its capacity, 0, 0, 0 will be shown. After that, some number, this one you don't need to worry, some number will be shown. That is what the point. That's why whatever the switch range is there, more than that you are observing, more than that you are giving, 0 will be observed automatically. Clear? Right. Prashant. Sir, in 3-digit voltmeter, only digits only, 2 digits only visibility. What is your question? In 3-digit voltmeter, 3 digits must be displayed. 3 digits must be visible. Why only 2 digits? Prashant Gopal Jhala. Prashant Gopal Jhala. Clear? Right. Now, coming to the topic. So this is the total discussion regarding 3-digit DVM. Okay. Now, in this 3-digit DVM, right, what is the resolution? What is the resolution formula? Concentrate. Resolution formula generally R is equal to, generally we say full scale value by number of divisions. Other people, newcomers, don't worry. This is a general formula, but I'm giving new formula for electronics model. Sir, full scale value is constant or varied with the switch position? Varied. So therefore, what I'm writing, simply 1 into scale range. This scale range depends on our selection. I may be using switch A according to my requirement. You may be using switch B according to your requirement. Your friend may be using switch C according to their requirement. So therefore scale range. But sir, in this device, do you have number of divisions like 1, 2, 3, 4? No. Which are there? Number of counts are there. So how many number of counts are there in 3 digit? 1000. So therefore 1 into 10 power 3000 counts. Where otherwise I'm writing here n, universal formula, 10 power n. N is number of digits. How many digits are there? 3 digits. So 10 power 3000, 1 by 1000. Yes, 1000 counts only there. This is the formula. But sir, is it valid or not? Is it valid or not? Let us prove with the example. Kindly concentrate. Simply we have built up the formula, but is it correct or not? Let us check. Sir, 1 volt range I'm taking. Concentrate. 1 volt range. Okay. Resolution equal to 1 by 1 into 10 power n means 3. Scale range, how much? 1 volt range. 1 by 1000. 1 millivolt. Go back and verify. Sir, switch A position. Switch A position. 1 volt range. Resolution is 1 millivolt. So therefore, we have got the same thing, 1 millivolt. So therefore, our formula is correct. Okay, second. 10 volts range. R is equal to 1 by 1 into 10 power 3 into 10 volts range. 10 millivolt. 10 volts range. 10 millivolt. Yes, 10 millivolt. Check it. Switch B operation. Switch B. 10 volts range. 10 millivolt is the resolution. Therefore, our formula is correct. So therefore, from now onwards, use this formula in order to find out the corresponding resolution. This is the total discussion regarding 3-digit division. This is a total discussion regarding 3-digit division. Clear, guys? Right. Now, I'm clarifying all the people's general doubt. Sir, if something is given, something is chosen, what will happen, etc. etc. Kindly concentrate. Very, very simple. One example I'm taking. 5 more minutes. Don't type anything. What are the typing time is there? That is over. Kindly again 5 to 10 minutes. Kindly listen. Suppose my value is, suppose my value is 0.454 volt is there with me. Some value. Actually, we don't know, but explanation purpose I'm taking as a known value. So 0.454 is there. Okay. Sir, which switch position is best? A position or B position or C position? Let us verify. Don't type any answer. Don't have any doubts because I am not started. Kindly concentrate. Now, in this I'm verifying. People are having the doubt. So 0.45 means 0 to 1 we can choose, 0 to 10 we can choose, 0 to 100 also we can choose. So which like that some conflict, but the confusion is there. With the confliction, the continuation topic also will be missed. So that's why concentrate. 0.45 volt. Now convert this into millivolt. 454 millivolt. Okay, right. Sir, a simple example. Switch A position I'm choosing without knowing anything. I don't know anything. Simply I'm choosing the switch A position and I'm giving this input. How will be the display? Concentrate here. How will be the display? That's what I'm taking. Sir, switch A, what is the count value? Switch A, the count value is 1 millivolt per count. Means 1 count equal to 1 millivolt or 1 millivolt equal to 1 count. Yes or no? So therefore, concentrate here. Sir, 1 millivolt produces 1 count. Kindly concentrate. Don't type anything. If you type 100%, you will be missing this topic. 0.454 is not known. but explanation purpose I'm taking as a known value. Okay, blindly I'm choosing switch A position. We don't know, just we are verifying 1 millivolt per count. So how many millivolts is there? 454 milli. 454 milli is there. Switch A gives 1 millivolt per count. Therefore, how many counts will be there? 454 counts. Sir, 3-digit DVM full scale counts are 1000 counts, but our input is producing 454 counts only. Acceptable, no problem. Not more than 1000, so acceptable. Okay. So switch A means decimal point 000 volt. Starting. How many counts? 454 counts. Okay, one count is there. Actually, 1, 2, 3, 4 will not be there. 454 cumulatively counted. But explanation purpose, I'm taking one by one. One count, second count, third count, fourth count. Like that, keep on going. 454 counts. What will be the number display? 0.454 volt. Yes, this is the display. If you choose switch A position. Okay. Now, let me complete. Switch B. Switch B. Sir, switch B, what is the count? 10 millivolt per count. That's a universal construction based. So therefore, switch B, 10 millivolt per count. 10 millivolt per count. Okay, 10 millivolt per count. Sir, 454 millivolt is there. 10 millivolt produce one count. How many counts will be there? 45.4 counts. Kindly don't ask how you are getting 45.4 mathematics. But 10 milli, one count, 454 milli, how many? First of all, 45.4, 0.4 count, 0.6 count will be there, will not be there. Yes or no? So 45 counts on. Okay. So switch B, 0.00 volt. Okay. One count, 0.01. Two counts, 3 counts, okay, 10 counts, 20 counts, step by step I'm taking, 40 counts, okay, like this. Finally, 45 counts are there, for example, 0.45, 0.45 volt. So after 45 counts, do we have 46th count? No, simply 0.4 means actually this count will not be there, but I'm giving full clarity here. So 0.45 is displayed. Okay. Now let me take the third position. Then I will explain the concept. Switch C. Okay. What is the switch C position? Here, 100 millivolt per count. Okay. 100 millivolt per count. Okay. So 454 millivolt supply we are giving. 100 millivolt produces one count. 200 millivolt, two counts. 300 millivolt, three counts. 400 millivolt, four counts. 500 millivolt, five counts. But 500 milli is not there. So therefore, 4.54 counts. Actually speaking, this is wrong representation. I need to write 45 counts only. But people ask that, sir, what happened to 0.4? That's why I'm showing this. But you need to understand that, okay, 45.4 count means 45 counts only. 4.54 count means 4 counts only. That logic you have to follow. Okay. Now, 0.0 is a starting display in switch C. Sir, one count, two counts, three counts, four counts. Okay. So therefore, what we can say, 0.4 volt. This is the display. Okay. Now tell me, sir, many people doubt is this. 0.454 is below 1, below 10, below 100. But which must be chosen? Now you tell me which is the best display. All are correct, but which is the best display? 0.454. 0.454 as it is. 0.45 values almost same. 0.4 values almost same. But which position is to be chosen for better representation? Means switch here position. Clear? Some people ask that, sir, if it is going more than etc. This was a simple discussion. I hope more clarity is available in this. Clear? Okay, right. Now I'm giving one more example in the reverse way. Then other doubt also will be clarified. These actually, this should not be written like this. But for clarity purpose, I'm showing 45 counts only you have to write. 4 counts you have to write. But idea purpose, I'm using all the digits. Okay. Suppose next number I'm taking as 1.45 volt. This is there with me. We don't know, but I'm taking as a known value. So 1.45 means convert this into milli. That's better, always clarity purpose. 1450 milli. Have it clear? 1450 milli. Right now, I'm taking switch A position. Switch A position. Sir, switch A. What is the count? 1 millivolt per count. This you have to follow compulsory. I'm not saying that remember, by heart, bug up. No. Switch A 1 milli. Switch B 10 milli. Switch C 100 milli. That's what the resolution you have to remember. Okay. Follow. And sir, 1450 millivolts is the input we have given. Unknowingly, blindly, I don't know any concept. I don't know. I'm a layman now. I don't know anything. Switch A, I'm trying. What is a switch A count? 1 millivolt per count already defined. 1450 millivolt means 1450 counts will be there. Blindly we can say 3-digit DVM means full scale counts itself 1000, but we are producing more than 1000. Automatically we can say 0 is a display. How? Let us verify. Decimal point 000 volt. Okay, sir, 1000 counts are there. 999 is there. More than 1000. What is that? 0, 0, 0 over. But don't think that, sir, next 1001 count 1002 it will be continued. No, this is called as a reset. This is called as reset. You may be thinking that it may be continuing like this. If it is continuing like this, means it is having the capability to allow more than 1000 counts. How it is possible from 3-digit device more than 1000 counts? Not at all. So that's why what we will display now? Simply 0.000 volt only. Right? In the laboratory, this is a general idea. The moment you observe this 0.000, but input is given simply okay. Range selection is less, given value is more. Therefore, I need to increase the range. Yes. Second case, I'm increasing the range position. I'm not increasing according to my wish. Designed range only. Switch B, 10 millivolts per count. Sir, 1450 millivolt is the given input. 10 millivolt produce one count, means 145 counts. Okay, again 0.00 volt, one count, 10 counts. Okay, 100 counts, 1.0, like that. If you're taking 145 counts, means automatically you will be getting 1.45 volt. Clear? Next, switch C. Switch C. What is the count? 100 millivolt per count. Sir, 1450 millivolt, 100 millivolt per one count. Okay. How many? 14 point, actually 14 counts only, but I'm writing clarity purpose. 14.5 counts. Okay. With this, don't fight with your digital faculty. 14 counts only, but I'm not leaving any number for clarity purpose. Now, 0.0 volt. Okay. Now, sir, one count, 9 counts, 10 counts, 11 count, 12 count, 13, 14. What's the number display? 1.4 volts. Now tell me, all are same. This is anyway not selection because that is more than its capacity. Now tell me, these two are mathematically good. 1.45 or 1.4, no problem. But which is better to prefer? Obviously, switch B is what actual logic. Wherever you require, wherever you're getting more clarity in the display, that you have to prefer. Yes, 1.45. This is the total discussion regarding entire digital O2 bit, that is 3-digit digital O2 bit. Right, step and count both are same, Bhavana. Step and count both are same. Already I have written here. Step and count both are same. Here, step or count. One step, one count, both are same. So this is the total discussion regarding entire 3-digit. I hope now everything is clear, because all types of explanation I have given with different examples. No. Vamshi, Maya, yes, more than 1,000 points, it won't affect the device, means it won't affect the device. No need to worry. No need to worry. But if you are giving too much heavy value, then that is a problem generally. So that's why account our range, account the instrument capacity, we need to choose properly. Jayesh Gupta, how do we define sensitivity? Right? Sensitivity is defined as the ratio of delta output by delta input. Change in output by change in input means if you are giving small change in the input side parameter, output should be responding, output should be available accordingly. Then we can say high sensitivity. Otherwise, low sensitivity. Is it clear now? Am I clear, guys? Can you let me know? Right. Sir, in switch C, can we get 14.5 value? No, sir. How do you get 14.5? How do you get 14.5? That's why I told you, simply count based. One count. This is 0, 0, 0.0. People are getting still doubt. That's why while I'm explaining, listen carefully. One count, right? Two counts, 9 counts, 10 counts, 11 counts, 13 counts, 14 counts. There is a question of 14.5. Who is this? Kavyasri. Is it possible? You only answer. Is it possible here? Definitely no. Is it clear? Okay, right. Everything explained clearly. No need to worry. Go after the class. The recorded video is available in the OTS platform. You can watch it again. Right. Now, this I'll be introducing the 3.5 digit. After that, again, we'll be having a doubt session as usual, and we'll end up the session. Right now, this is 3 digit. Now, the next device is 3.5 digit DVM. Right. Kindly concentrate. Kindly concentrate. Navin Sai. Right. Navin Sai. Sir, if we use this 3-digit DVM for application like excitation control, the input will be continuously changing for a generator. Will this be a good one to use there? Kindly concentrate. Wherever the input is varied continuously, but for a particular input, it will show particular value. So no need to worry, you can use it. No need to worry. Right? If that is the case, no one instrument can be used, right? N-log also, what is it? It is keep on getting changed. That's why for a particular value, it will show a particular value. That's not the point. Right. See, protection for DVM, etc. We are not going beyond the value. According to that value only, we have to use it. So no problem. Right? Right. Tomorrow's class timing, Shreyas Sasi, 5 to 9. Tomorrow's class timing is 5 to 9. 1 second. It is not at given, but it is 5 to 9. Tomorrow's schedule is 5 to 9, he told. And if any change in information, change in schedule is there, you will get the information. No need to worry. Tomorrow's schedule is 5 to 9. Okay, right. Kindly concentrate. 3.5 digit DVM. Very, very simple. So in this device, 3 full digits will be there. Again, some other new terminology. 3 full digits. What is the meaning of full digit? First of all, what is the meaning of full digit? Right? The full digit means 0, 1, 2, so on up to 9. If any digit is designed to allow, 0, 1, 2, 3, 4 up to 9, then that is called as full digit. This is the definition. Kindly don't come in the reverse way, like, sir, people are asking this question, why the full digit allows 0? Not like that. If a digit is designed to count from 0 to 9, then the digit is named as full digit. Okay, now tell me, whatever the discussion you have taken so far, 3 digit DVM, is it 3 full digit? Yeah, 3 half digit means 3 full only. Clear? Okay. So in order to count 0 to 9, which type of counter we have to use? Mod 10 counter, yeah, decade counter. Generally we can say yes. DC we can say, mod 10 counter we can say. Already we have taken this 3 digits, same thing. But now the new part here is half a digit. Half a digit. So what do you mean by half a digit? Full digit means okay, like this. But what do you mean by half a digit? Very, very important. Half a digit is a digit. Half a digit is a digit, right? Which allows, which is designed to count only 0 or 1. Only 0 or 1. Again, I'm giving, sir, half a digit means why only 0, 1? No. If any digit is designed to count only 0 and 1, then that digit is named as half a digit. The digit is named as half a digit. That's what the definition of half a digit. Clear? Clear? Right, sir. In order to have the full digit count, we have taken, what is it? Counters, the 3 numbers. 3 numbers. Why? 1 full digit, 1 full digit, 1 more full. So 3 counters. Sir, in order to count 0 and 1, which type of device we have to use? Tell me, everyone. Which type of device we have to use? If you are using mod 10 counter, that will count from 0 to 9. But we need to have the count from 0 and 1 only. 0 and 1 only. Then which must be used? Tell me. Okay, Abhijit, binary counter. Gokul Sham, flip flop. Very nice, very nice. Imtiaz Pasha, binary counter. Shilpa, flip flop. Very good, very good. Simple logic, yeah. I am asking the question for that purpose only. Many people are saying that don't write binary counter. Come on, yeah. Not binary. Binary counter means 0. Weight of base weight is 2. 1 is also base weight is 2 only. But our number is which one here? 0. What is it? 999 means, is it 2 power 0 weight? No. 10 power 0. 10 power 1. 10 power 2 weight. So that's why our base is 10 only. That's why don't say, this is the general thought with almost many students. 0, 1 means blindly binary. No, yeah. In the binary, 0, 1 is there. In the octal, 0, 1 is there. Decimal, 0, 1 is there. Hexadecimal also 0, 1 is there. The moment you are observing 0 and 1, sir, binary simply. No, yeah. Here weight is 2, weight is 8, weight is 10, weight is 16. But what is our system? Decimal system. That's why this 0 is decimal 0. This 1 is also decimal 1 only. That's why come out of the thought like 0, 1 binary always. No. 0, 1 is there in every system. Based on the weight, you need to concentrate. Okay. Now tell me, which must be means simply toggle flip-flop. Toggle flip-flop. T flip-flop will be given. Means the T flip-flop will be counting 0 or 1 only. If the input is not given, suppose output is 0. If it is activated, 0 becomes 1. Again activated, 1 becomes 0. Again activated, 1 becomes 0, 0 become 1, 0, like that, continuously varying. But is it possible to have number 2 from the toggle flip-flop? No. So that's why toggle flip-flop is used here. But you may be asking, sir, why don't we use mod 2 counter? You can use mod 2 counter, no problem. You can use mod 2 counter, no problem. Clear? Kindly don't say Shruti Ghodke. Kindly don't say positive, negative. Don't say high, low, you say generally. High 1, low 0. But that is binary model. But our digit is 0, 1 value is there. 1, 1 value is there. So that's why 0, 1, 0. Of course, your thought is correct. Positive, negative means reverse process you are saying, but don't say that. Okay, right. And after that, I will be writing these 2 points in the tomorrow's class after explanation. What is it difficulty? Now, here. It's a 3.5 digit. How it looks like? Three full digits, 1 half a digit. 3 full, 1 half a digit. But be clear, sir, what is the meaning of this? 0 to 9. Nothing but 1 mod 10 counter decade. 0 to 9. 0 to 9. Okay. These three are called as full digits. Why? These are designed to allow from 0 to 9 counts, all 10 counts. Okay. But here only 0 and 1. Not 0 or 1. 0 and 1. Okay, 0 and 1. Now tell me, concentrate here. Sir, what is the starting display? 4 zeros. Starting display is 4 zeros. Okay, sir. First step or first count? Okay, if it is keep on going, up to which value it will go? Up to which value it will go? Everyone answer. Up to which value it will go? Respond. Very nice, very nice. Yes. So it will go up to 1,999. Therefore, how many counts? 2,000 counts. Sir, in the earlier case 1,000, here 2,000 means automatically range is extended or not. There up to 999 only. Therefore, 1,000 counts. But here it is 1,999. So therefore, 2,000 counts. So therefore, by adding the half a digit, by adding this extra digit, the range is extended. Yes, I'm writing that point. Range is extended. Other point with expression I'll give you. So this is what the simple idea regarding 3.5. But don't ask any question at 3.5 because only introduction I have given. Tomorrow we are going to take in detail explanation. We are going to take all varieties of questions. Okay, I'm stopping now. If any doubts are there, you can clarify. Sorry, you can ask, I will clarify. But one thing, people are asking one question irrelevantly. What is it? Suppose if you're studying about DC machine, DC motor means DC supply is given, converted into AC, that is converted into mechanical output. That will you think of. So if AC is given, what happens? Don't go like that. First, what is the operation that you give it first? In that you think first. But many people are leaving the actual thing and asking about, so that is given, this is given, etc. Yet those doubts will be clarified automatically when you understand the actual topic. That's what the point. Okay. Any doubt is there? You can talk to me.
Hello, good evening, sir.
Yeah, who is this?
Ramakrishna.
Ramakrishna. Yeah, tell me.
That same thing, sir, that regarding the average of square wave. Can you draw a square wave? Can I ask it out?
Square wave average value. I'm not
Yes,
getting.
yes. Yes, sir. You have said that square wave average value is Vm, no, sir.
That you asked in the network theory class. Arre, come on, yeah.
No.
I'm explaining. Don't need to worry. See,
Okay. So
square wave average
yeah.
value 0. Okay. So what
Okay.
about sine wave average value?
Sine wave average 0, sir.
Right? Then
Yes,
what
sir.
you have to do? If you are getting average value of a full cycle is 0, what you have to do? Network theory, very, very important point in the 4th chapter. AC circuit analysis. In the network theory booklet, it is there. What you have to do?
Incomplete networks.
Right?
So I don't.
One second. V average is equal to Vm by pi or 2Vm by pi. We write it based on the cycle. How do you write this? Tell me.
Okay, this is based on the rectifiers by changing.
No. Answer my question. Positive,
By
negative.
taking a half cycle.
Then here also,
Okay.
by taking half a cycle, you will get V average is equal to
Okay,
Vm.
sir.
That's it.
Okay, sir.
Right? That's
Okay,
right.
I was taking full cycle, so why I was
No.
thinking like that.
All the simple logic here. Who is this? Ramakrishna, right?
Ramakrishna,
See,
yes, sir.
yeah, simple logic. If you are having the symmetric waveform,
Then-
always half a cycle. Asymmetric waveform, full cycle, blind
Full
logic.
cycle, yes. Okay, sir.
Finish.
Thank you, sir.
Yeah, good evening, sir.
Is this Sahil?
Yes, sir.
Yeah.
Sir, my doubt regarding, sir, full scale deflection current, sir.
Full scale deflection?
Current, sir. Full scale deflection current, sir. Sir,
I'm not understand.
full scale deflection current means the maximum current of the instrument, sir.
Yeah, simple. 0
Sir,
to 10.
Sir,
0 to 10.
this is the, sir, maximum current, sir, but average current always not the maximum current, sir. Why we are taking always I average equals to I FSD,
You
sir?
are missing again. I am not taking I average equal to IFSD blindly. What is our discussion?
RS, sir.
Yeah, whatever the I average flowing through the PMMC should not exceed its full scale deflection. That's why
Okay, sir.
whatever the current is flowing, that should be equal to IFSD, not more than IFSD. Then how much resistance is to be kept? That's what the point.
Okay, sir. Means I average always not equal to the IFSD, sir.
Normally not equal, but in this, whatever the I average is flowing, okay, 5 is flowing, save device, 6 is flowing, save device. Suppose its full scale value 10, more than 10 is flowing, damage. That's why the current should not flow more than 10 if it is a 10 full scale. How much RS is to be kept? Right?
Thank you, sir.
Hello, sir.
Yeah. Pratyush?
Yes, sir.
Yeah, tell me.
In 35F, sir.
Huh?
In 35F, sir. 35F slide.
Yeah.
Sir, in this, first the meter is calibrated for sine wave.
Yes.
Yes, no, sir. Then we have given triangle wave so that there is some error, no, sir.
Yeah.
Sir, if we give pure sine wave again, there will be no error, sir. No error, no, sir.
No error
Okay,
means measure related no error, but corresponding connection related errors will be there. But generally no error we say, calculation pointer. Good question.
Yes, sir. Sir, if you want to measure any square or triangular wave, we have to calibrate according to that square wave or triangular wave average values, no, sir.
No. You need to calibrate mathematically, but practically available devices are only for sine wave. That's why if you give some other waveforms, automatically error will be, that is called as waveform error. But if you're keen about, sir, I'm having square wave, can I calibrate for square wave? Yes, you can calibrate. That's what.
Then the error will be less, no, sir. If we calibrate for a square wave.
Definitely.
Oh,
but
yeah.
Standard signal is sine. That's what my point.
Yes,
If
sir.
you
Yes,
want-
sir. Yes, sir.
Got it?
Yes, sir. For more number of signals are sine waves, so we calibrate only for sine waves.
That's a very good question, because 99% of the systems are working with sine only, square wave or etc. Peculiar applications only, smidge trigger or multi-wave, etc. There we go for. That's all.
Okay. Sir, normally these rectifiers are only uncontrolled rectifiers only, sir. In practical case, also.
Different diode based only. But if the technology is being developed, no, we can go for thyristor, but measurement point of view simply uncontrolled diode only.
Oh, okay, sir. That's it, sir. Thank you, sir.
Right.
Hello, sir.
Yeah.
Sir, you are told in the half-wave rectifier waveform, we have to consider the RMS voltage of the input side.
Yes. Tell me, Avinash.
Sir, you are told in the half-wave rectifier waveform, sir, in PMMC concept, sir, actually.
I'm not
We have to consider
understanding.
the RMS voltage of the input. Hello, sir.
One second. Yeah, tell me.
Sir, here, sir. Sir, while finding the power, form factor, sir, we have considered the RMS value of the input voltage.
Yes.
Sir, here I have not got, sir, means how we have find the form factor expression.
How we are finding
Form factor expression, sir.
form factor expression? Where?
Yes.
Here?
Yes. Yes, sir. That's like previous one. Yes, sir. Yes, sir. Yes. Yes, sir.
Yeah.
Sir, the previous one.
Yeah.
The previous
Hmm.
one slide.
So your
yes,
doubt
sir.
is
Sir, here
why
we have
we are
considered
taking this
RMS
RMS value, right?
Yes, sir. Yes, sir.
Simple logic. Yeah. All I told you here. Now tell me, this PMMC shows average value, okay, of this waveform. Now this average value should be
Yes.
converted into this RMS value or its RMS value. Tell me.
Yes. Input RMS value, sir.
Then that's what I have taken here.
Sir, why we have taken that? That's what.
Huh?
Sir, why we have
Hello?
considered it actually?
Come on here. What is your unknown? What is your unknown? Which is your unknown?
Sir,
Avinash,
we input, sir.
this only, right? So therefore, whatever the shown value is there, it should be converted this into this RMS because this is what our unknown. Whatever unknown parameter is there, that only we have to determine. So that's why our unknown is this. Therefore, we are determining this value. That's why this is not to be converted to this. Suppose, let me take this is converted to this one. Is our measurement process completed? No. Why? This is our unknown. That's why this should be converted into this. That's why I gave you this here.
Okay, okay, sir. Yes, sir.
Yeah, Mukul.
Sir, can you explain loading effect one?
Loading effect, I will explain later. No need to worry. That will be coming later. Simple logic. Error due to internal resistance of the meter. Definitely, every device has one resistance, right? Due to that resistance,
Yes,
power consumption will be there. Therefore, the error will be there, simply called as loading effect. Enough. But
no.
I'll explain in the measurement. No, electrical, no need to worry. Okay.
And sir, why are you considering only voltmeters always in
No, no.
digital
No,
as well as
No,
analog?
no. Actually, the syllabus itself is digital voltmeter. Generally, in the electronic category, generally voltage measurement only will be most. That's why you can go for ammeter also. Multimeters are there, but in the syllabus voltage, that's why I'm taking voltmeter. That's it. In the multimeter, voltage will be there, current will be there, resistance will be there, etc. Okay.
MACDCL install as a digital meters. So
Yes.
can we say the operation is same?
Huh?
Sir, I recently MACDCL installed as digital meters in our houses
Energy meter, right?
in Maharashtra. Yes, sir. So that is it same for as that of voltmeters?
Same thing.
Whatever
Very
we
good. In the digital instrument, now we have taken no counters. There we have taken some gearing pin and mechanism. That's it.
Oh, okay. Okay, that's all. Thanks.
Okay. Right. Any more doubts? I think no raised hands. So can your mobile phone number? Yes, I'll give you. Mukesh, no need to worry. Pranjali, sir, can you please repeat waveform? Simple logic here. Sine waveform calibration is there already. If I give some other waveforms, definitely that waveform is not having the same form factor of sine wave. Error belief, that is called as waveform error. Very, very simple. That only I gave the note here. Here I gave the note. Here. Rectifier type instruments are calibrated for RMS values of sine wave. Means the calibration is for 1.1 mean into average, yeah, 2.22 into average. But if you are giving square wave or triangular wave, definitely error. That is called as waveform error. Simple. Yeah, notes will be uploaded as soon as possible. No need to worry. Right. So this is my number. But if you are sending any question, kindly you try it. After that only kindly send me. Otherwise, so many hundreds of people are there. No, if everyone is sending 5, 4 questions, difficult to reply. That's why you try it first. Again, try it again. Then you send me. Okay, if there is no doubt, we can conclude.
Hello, sir.
Yes, who is this?
Sir, Mukul here, sir.
Yeah.
Can I get your qualification?
Can I get your?
Qualification.
I'm not getting.
Your education, sir. I
Okay.
mean,
You do you want me to get that? Okay, I'll give you. Why here, Mukul?
no, sir. You don't tell.
Yes,
I attend your 3 lectures. You don't tell that.
I'm not getting. Little bit louder.
No, sir. Just for the knowledge.
Just for okay, going
No.
purpose. Okay, no problem. I'll give you clear thing. I'll show everything clearly so that you can get idea.
Okay.
Is it okay?
Yes, sir. Got it, sir. Sir, from where you did your MTech PhD?
In our state only, Telangana state only.
Okay, sir. Okay.
Right.
Thank you, sir.
Okay, then tomorrow 5 o'clock is a general schedule. If any change is there, they will let you know. What are the types of A to D converters and the basics of speed? Our topic is not related to speed. You are having servo type, etc., etc. But our topic is based on the conversion one only. But that A to D converter is not there in the GATE syllabus. In the ES it is there, but tomorrow I'll take that A to D converter. What will happen in the with you? Right, Mukesh, yes, I have a simple clarification. What is your clarification, Mukesh? Yes. So generally, Akshay, generally damage will not be there, but internet disturbance though definitely rahega. But generally, based on the selection, we need to use. Otherwise, what happens? Internet, fuse will be broken, so fuse will be blown out. Then again, fuse will be connected, etc. Will be there. Definitely, small problem, but corresponding protection will be there. Okay, Mukesh, yes, small clarification. Okay, tell me.
Hello, sir.
Yeah.
Sir, in our AS Academy book, they have given analog voltmeter is for ESC students. And in textbook, they have not given the syllabus for GATE, sir.
No. Everything, whatever the thing you require, I'm giving that totally. You are GATE student or ESC student?
GATE student, sir. In our textbook, analog voltmeter is not there, sir. Concept is not.
Yeah. See, in the GATE, actually, they have not mentioned analog voltmeter specially. and the two they are giving the questions in 2 years once or 3 years once, etc. That's why that is not according to syllabus. It is not given, but sometimes they're asking the question. That's why. And syllabus point of view means order point of view. I'm going. No need to worry.
Okay, sir.
Whatever the topic you require, everything I'm giving. So more than this, not required. Don't worry.
Okay, sir. Thank you. Thank you.
Okay then. Yeah, Bhavana Masa, right? Correct. Full scale means maximum value of current measure. Correct. Okay. Pratyusha, good night, sir. Okay. Okay, right. Good night. Tomorrow we are going to meet. We are going to continue the 3.5 digit DVM, and we are going to take questions, and we are going to start next chapter also. Good night, everyone. Thank you.
Good night, sir.
Yeah, good night. Good night. Thank you. Who is this? Right.